Before we can ask what happened before the Big Bang, we must first confront a strange possibility. What if the question itself breaks the rules of reality? Every experience you have ever known exists inside time. Every memory, every thought, every star, every galaxy unfolds from one moment to the next. Time feels so fundamental that imagining its absence seems impossible. Yet according to our best understanding of the universe, time itself may have begun with the Big Bang. If that is true, then asking what came before it might be like asking what lies north of the North Pole. There may be no earlier moment because earlier did not yet exist. But this answer, while elegant, leaves many people unsatisfied. Human curiosity refuses to stop at a boundary. If time began at the Big Bang, what caused time to begin? What created the conditions for existence itself? For centuries, philosophers, scientists, and dreamers have wrestled with these questions. Ancient civilizations imagined cosmic eggs, eternal oceans, divine creators, and endless cycles of destruction and rebirth. Modern physics has replaced mythology with mathematics, yet the mystery remains just as profound. The Big Bang is often misunderstood as an explosion in space, but it was actually the rapid expansion of space itself. Everything we can observe today emerged from an unimaginably hot, dense state nearly 13.8 billion years ago. As we trace cosmic history backward, temperatures rise, distances shrink, and the laws of physics become increasingly extreme. Eventually we reach a barrier known as the Planck epoch, a realm so small and energetic that our current theories collapse. Beyond that point, certainty disappears. The equations that describe reality cease to function. The universe hides its deepest secret behind a wall of physics we do not yet understand. Somewhere beyond that wall may lie the answer to what came before the Big Bang, or whether there was ever a before at all. This journey takes us to the edge of knowledge itself, where cosmology meets philosophy and where some of the greatest mysteries in science still wait to be solved. To understand what might have existed before the Big Bang, we first need to travel back to the earliest moments that science can currently describe. Imagine the entire observable universe compressed into a state so dense and energetic that every atom, every star, every galaxy that would ever form existed only as potential. In the first tiny fraction of a second after the Big Bang, reality looked nothing like the cosmos we see today. There were no planets, no light-filled skies, no structures of any kind. Instead, the universe was a seething ocean of pure energy. Temperatures exceeded anything imaginable, reaching trillions upon trillions of degrees. Under such extreme conditions, the familiar forces of nature behave differently. Gravity, electromagnetism, and the nuclear forces may have been united into a single fundamental interaction. Matter as we know it could not yet exist. Even the distinction between particles and energy becomes blurred. Physicists call the earliest known period the Planck epoch, lasting less than a trillionth of a trillionth of a trillionth of a second. During this era, quantum effects dominated every aspect of existence. Space itself may have fluctuated violently, appearing less like a smooth fabric and more like a chaotic foam. Tiny regions could have appeared and disappeared continuously. Distances smaller than the Planck length lose their conventional meaning, and our current equations fail to provide reliable answers. This limitation is not merely a technical problem. It represents a fundamental gap in our understanding of nature. General relativity, which explains gravity on large scales, and quantum mechanics, which governs the microscopic world, refuse to cooperate under these conditions. Both theories work remarkably well within their own domains, yet when pushed into the extreme environment of the universe's beginning, they produce contradictions. Scientists believe a deeper theory, often called quantum gravity, is needed to bridge this divide. Until such a theory is discovered, the earliest instant of cosmic history remains hidden. The Planck epoch acts like a curtain drawn across the first scene of existence. We can see hints of what happened afterward, but the opening moments remain concealed. This uncertainty is precisely why the question of what came before the Big Bang remains one of the most fascinating mysteries in science. If our theories cannot fully describe the beginning, they certainly cannot yet tell us with confidence what, if anything, preceded it. Yet this very ignorance has inspired some of the boldest and most imaginative ideas ever proposed in cosmology. One of the most surprising possibilities is that the universe never truly had a beginning at all. While the Big Bang is often described as the birth of everything, some cosmologists argue that it may instead represent a transition from an earlier state of reality. In this view, the Big Bang was not the first moment of existence but merely the beginning of the universe as we currently know it. Imagine reading a book and opening directly to the middle chapter. The story begins there from your perspective, yet countless events occurred beforehand. The universe may be similar. The apparent starting point could simply mark the limit of our observations rather than the true origin of reality. This idea has attracted scientists because it avoids some of the difficult problems associated with creation from nothing. If something existed before the Big Bang, then perhaps the cosmos evolved naturally from earlier conditions. Various models suggest different possibilities. Some describe a universe that contracts before expanding again. Others propose a timeless quantum state that eventually gives rise to space-time itself. There are even theories in which countless universes emerge continuously from a larger cosmic structure. What makes these ideas compelling is that they attempt to extend physics beyond the apparent boundary of the Big Bang. Instead of treating it as an absolute beginning, they view it as a transformation. This approach resembles many discoveries in the history of science. Boundaries that once seemed fundamental often turned out to be signs of incomplete understanding. Ancient people believed the horizon marked the edge of the world. Later generations learned that it simply reflected the limits of perception. Likewise, the Big Bang may eventually be understood not as the ultimate beginning but as a horizon beyond which deeper layers of reality exist. However, this possibility introduces new questions. If something came before the Big Bang, what was its nature? Did time already exist? Were physical laws the same as they are now? Could there have been stars, particles, or dimensions unlike anything familiar? Every answer seems to generate even more mysteries. Yet this endless chain of questions is part of what makes cosmology so fascinating. The deeper we explore the origins of existence, the more we realize how little we truly know. The universe continues to challenge assumptions that once seemed obvious, forcing us to rethink concepts such as time, space, causality, and even reality itself. Perhaps the greatest lesson from modern cosmology is that the beginning of our universe may not have been the beginning of everything. It may simply be the oldest chapter we can currently read. One of the oldest and most fascinating ideas about what came before the Big Bang is the possibility that the universe operates in endless cycles. Instead of imagining a single beginning followed by a single future, some cosmologists have proposed that reality may pass through recurring phases of birth, evolution, collapse, and rebirth. In such a universe, the Big Bang would not represent the ultimate beginning of everything. It would simply mark the start of the current cycle, much like sunrise marks the beginning of a new day without being the beginning of time itself. This concept has deep historical roots. Long before modern science emerged, many ancient cultures envisioned time as cyclical rather than linear. Seasons repeated, generations rose and fell, and celestial bodies followed predictable patterns across the sky. It seemed natural to imagine the cosmos itself participating in similar cycles. Modern physics, surprisingly, has occasionally revisited this ancient intuition. Certain mathematical models suggest that our expanding universe could eventually stop growing and begin contracting. If gravity was strong enough to overcome expansion, galaxies might slowly reverse their motion and move toward one another. Over billions or even trillions of years, the cosmos would become increasingly dense and hot. Eventually everything could collapse into a state resembling the conditions often associated with the Big Bang. This hypothetical event became known as the Big Crunch. In the simplest version of the cyclic universe model, the Big Crunch would not represent an ending. Instead, it would trigger a new expansion phase, producing another Big Bang and another universe. The cycle would repeat indefinitely, with no true beginning and no final end. The appeal of this idea is immediately obvious. If every Big Bang emerged from a previous cosmic collapse, then there would be no need to explain how existence suddenly appeared from absolute nothingness. Reality would be eternal, continuously transforming from one state into another. Questions about ultimate origins might become unnecessary because there would never have been a first moment. Every universe would have a predecessor stretching endlessly into the past. Yet while elegant in principle, the cyclic universe faces significant challenges. One major problem involves entropy, a concept closely associated with disorder. According to the second law of thermodynamics, entropy tends to increase over time. Stars burn their fuel, energy spreads out, and systems gradually become less organized. If the universe has undergone an infinite number of cycles, scientists would expect entropy to accumulate from one cycle to the next. Over unimaginable spans of time, the cosmos should become increasingly chaotic and unable to produce the structured universe we observe today. This issue led many researchers to doubt whether simple cyclic models could accurately describe reality. Despite these difficulties, the concept refused to disappear. In the late 20th and early 21st centuries, new versions of cyclic cosmology emerged. These models were often inspired by advances in theoretical physics, particularly ideas involving extra dimensions. Some theories suggest that our universe may exist on a vast three-dimensional surface known as a brane floating within a higher dimensional space. In these scenarios, the Big Bang could result from collisions between enormous cosmic brands. Imagine two gigantic sheets drifting through a higher dimensional realm. When they collide, tremendous amounts of energy are released, creating conditions similar to those observed at the beginning of our universe. After the collision, the brands separate, only to gradually move back together over immense periods of time. Another collision eventually occurs, producing a new cosmic cycle. In this framework, the universe does not repeatedly collapse into a singular point. Instead, cycles emerge through interactions within a larger multidimensional reality. This approach avoids some of the entropy problems associated with older cyclic models while providing a fascinating picture of cosmic history extending far beyond the observable universe. What makes these ideas particularly intriguing is that they transform the Big Bang from an absolute beginning into a transitional event. The dramatic birth of our cosmos becomes one chapter in a much larger story. The universe we inhabit would be only the latest expression of processes operating across scales of time and space almost impossible to imagine. Entire cosmic histories could unfold between collisions. Galaxies would form, stars would live and die, planets would emerge, and civilizations might rise and disappear before the next cycle began. From this perspective, the Big Bang resembles a heartbeat in an eternal cosmic organism rather than a unique creation event. Some physicists find this vision attractive because it replaces the mystery of beginnings with a broader framework governed by physical laws. Instead of asking why the universe suddenly appeared, we ask how cycles operate and what deeper structures make them possible. Yet profound questions remain. If cycles truly stretch infinitely into the past, what mechanism sustains them? Why do the laws governing these cycles exist at all? Could every cycle produce slightly different physical constants? Might previous universes have contained forms of matter, stars, or even life unlike anything familiar to us? If information survives between cycles, could traces of earlier cosmic history somehow influence the present universe? Researchers continue searching for observational evidence that might support or challenge these possibilities. Some studies examine patterns in the cosmic microwave background, the ancient light left over from the early universe. Others investigate whether gravitational waves or large-scale structures might contain subtle signatures of events preceding the Big Bang. So far, no definitive proof has emerged, but the search continues. The cyclic universe reminds us of an important lesson in cosmology. What appears to be a beginning may not actually be one. Throughout history, humanity repeatedly discovered that apparent boundaries often reflected limitations in understanding rather than fundamental limits of reality. Horizons once thought unreachable turned out to be gateways to larger worlds. The edge of the solar system became the beginning of interstellar space. The Milky Way became one galaxy among billions. Perhaps the Big Bang itself represents a similar horizon. It may seem like the first chapter because it marks the limit of our current observations, yet beyond it there could exist an endless sequence of cosmic ages stretching far into an unknowable past. Whether this vision proves correct remains uncertain. But it offers a compelling answer to one of humanity's oldest questions. Perhaps before the Big Bang there was another universe, and before that another, and before that yet another, in a chain with no true beginning and no final end. Another remarkable possibility is that our universe emerged from the quantum vacuum, a concept that sounds deceptively simple but becomes increasingly strange the deeper one explores it. In everyday language, a vacuum is often imagined as empty space, a complete absence of matter and energy. Most people picture a vast dark void containing absolutely nothing. However, modern physics paints a very different picture. According to quantum mechanics, true emptiness may not exist at all. Even the most perfect vacuum imaginable is not silent or inactive. Instead, it is a restless sea of fluctuations constantly bubbling with temporary activity. Particles can briefly appear and disappear. Tiny bursts of energy emerge from seemingly nowhere before vanishing again. This bizarre behavior has been confirmed through numerous experiments and has become one of the fundamental features of quantum theory. The vacuum, rather than being nothing, appears to be a dynamic and energetic state underlying reality itself. Once physicists realized this, a fascinating question naturally followed. If small quantum fluctuations can produce particles, could an enormously rare fluctuation produce an entire universe? To understand why this idea attracts serious scientific attention, it helps to imagine the microscopic world revealed by quantum mechanics. At subatomic scales, certainty gives way to probability. Particles do not behave like tiny billiard balls moving along precise paths. Instead, they exist within clouds of possibilities described by mathematical wave functions. The universe at its deepest level appears fundamentally uncertain. Events that seem impossible from a classical perspective can occur if quantum laws allow a non-zero probability. This strange framework explains countless observations, from atomic behavior to the operation of modern electronics. Within this quantum reality, fluctuations are unavoidable. Even in a vacuum cooled to extraordinary temperatures and stripped of all matter, energy continues fluctuating. Space itself seethes with activity. Physicists sometimes describe this as a quantum foam, a constantly shifting landscape where virtual particles emerge and disappear in unimaginably short periods of time. Most fluctuations are microscopic and insignificant on cosmic scales. Yet given enough time and enough possibilities, some theorists wonder whether larger events could occur. One influential proposal came from physicists who argued that the entire universe might have originated as a quantum fluctuation. In this scenario, reality did not require pre-existing matter, stars, galaxies, or even conventional space. Instead, a tiny quantum event could have triggered the birth of spacetime itself. The idea sounds almost magical, but its supporters emphasize that it arises from mathematical principles rather than fantasy. Quantum mechanics permits fluctuations. General relativity describes how energy shapes space and time. When these concepts are combined in certain ways, they suggest that universes might occasionally emerge from quantum conditions. The Big Bang would then represent the rapid expansion of one such fluctuation. What appears to us as the birth of everything could have been the natural consequence of deeper quantum processes operating beyond our ordinary understanding. In this picture, the universe is not necessarily unique. Countless universes might arise over vast spans of cosmic time, each originating from similar fluctuations within a larger quantum framework. This raises an immediate philosophical challenge. If the universe emerged from a quantum vacuum, does that truly mean it came from nothing? Many scientists would answer no. The quantum vacuum is not equivalent to absolute non-existence. It possesses structure, mathematical properties, and physical laws. It is a state of reality rather than the absence of reality. Critics therefore argue that such theories merely shift the problem. Instead of explaining why the universe exists, they explain how one form of existence emerged from another. The deeper question remains: why does the quantum vacuum exist? Why do the laws governing quantum fluctuations exist? Why is there a framework capable of producing universes at all? These questions move beyond physics into philosophy, illustrating how discussions about cosmic origins often blur the boundary between scientific investigation and metaphysical inquiry. Nevertheless, the quantum vacuum model offers several appealing features. It avoids the need for a singular beginning where physical laws completely break down. Instead of imagining reality emerging from absolute nothingness, it proposes a natural process governed by known principles. Furthermore, quantum cosmology provides mathematical tools that allow researchers to explore conditions extremely close to the Big Bang. Some models suggest that time itself could emerge gradually from quantum states rather than appearing suddenly. Others indicate that multiple universes might constantly form within a larger quantum landscape. In these frameworks, our cosmos becomes one member of an enormous family of universes, each with its own history and characteristics. Some might expand forever. Others could collapse quickly. Some may contain physical constants radically different from our own. The vast majority might remain forever inaccessible, separated from us by the fundamental structure of space-time. The implications are astonishing. If universes can arise from quantum fluctuations, then reality may be far larger and more diverse than anything visible through telescopes. Every galaxy we observe, every star shining in the night sky, every planet orbiting distant suns would represent only a tiny fragment of a much greater cosmic tapestry. The observable universe itself could be merely one bubble among countless others. Entire realms might exist beyond our horizon, forever hidden yet equally real. Such ideas challenge traditional notions of uniqueness and cosmic significance. Humanity would not inhabit the only universe but rather one example among an unimaginable multitude. Despite its elegance, the quantum vacuum hypothesis remains speculative. Direct evidence remains difficult to obtain because events preceding the observable universe are largely inaccessible to observation. Scientists continue developing mathematical models and searching for subtle clues that might support or contradict these theories. Future advances in quantum gravity, cosmology, and particle physics may provide deeper insights. For now, however, the concept remains one of the most fascinating possibilities ever proposed. It suggests that beneath the familiar world of matter and energy lies a deeper quantum reality, endlessly active and creative, capable of giving birth to entire universes. If this vision proves correct, then before the Big Bang there may not have been stars, planets, or galaxies. Instead, there may have been a vast quantum sea of possibilities, from which our universe emerged like a wave rising briefly from an eternal ocean of potential. Among all the ideas proposed about what existed before the Big Bang, few are as astonishing as the concept known as eternal inflation. This theory does not merely suggest that something existed before our universe. It proposes that our entire observable cosmos may be only a tiny region within a far greater reality that has been generating universes for unimaginable lengths of time. To appreciate this idea, we must first understand inflation itself. During the late 20th century, cosmologists encountered several puzzling features of the universe. One of the most significant involved the remarkable uniformity of the cosmos. No matter where astronomers looked, distant regions of space appeared surprisingly similar. Temperatures measured across enormous distances were nearly identical, even though those regions seemed too far apart to have ever exchanged information. According to conventional Big Bang models, there should not have been enough time for distant parts of the young universe to coordinate their properties. Yet observations revealed a cosmos displaying extraordinary large-scale consistency. Inflation was proposed as a solution. According to this theory, the universe experienced an incredibly brief period of explosive expansion shortly after the Big Bang. In a fraction of a second, space expanded far faster than the speed of light, stretching tiny regions into vast cosmic domains. This rapid growth smoothed out irregularities and helped explain many observed features of the universe. Over time, inflation became one of the most influential ideas in modern cosmology. As researchers explored inflation more deeply, they discovered something unexpected. Certain versions of the theory suggested that inflation might never completely stop. In our region of space, inflation ended, allowing stars, galaxies, and planets to form. However, elsewhere the inflationary process could continue indefinitely. Imagine boiling water in a pot. Small bubbles form, grow, and separate from the surrounding liquid. In a similar way, regions where inflation ends could become individual universes embedded within a larger inflating background. While one cosmic bubble develops galaxies and civilizations, countless others continue forming elsewhere. New universes constantly emerge while the larger inflationary process persists. This concept became known as eternal inflation because the creation of universes never truly ends. The larger structure continues generating new cosmic domains forever. In this picture, the Big Bang that gave rise to our universe was not the beginning of everything. It was merely the birth of one bubble universe within an endlessly expanding multiverse. The implications are staggering. If eternal inflation is correct, then reality may be vastly larger than the observable universe. The region we can see through telescopes represents only a tiny island within an immeasurable cosmic ocean. Beyond our horizon may lie countless other universes separated by enormous distances. Some could resemble our own closely. Others might possess different physical constants, different particles, or entirely unfamiliar forms of matter. In certain universes, stars may burn differently. In others, galaxies might never form. Some may collapse rapidly after birth, while others could remain lifeless and empty forever. The diversity could be practically limitless. Every possible arrangement permitted by the laws of physics might exist somewhere within the multiverse. Our universe would then be one example among an inconceivably large collection of cosmic worlds. This idea offers a potential explanation for one of the most puzzling features of reality, the apparent fine-tuning of physical constants. Many properties of the universe appear delicately balanced. If the strength of gravity differed slightly, stars might never form. If certain nuclear forces changed even modestly, the chemistry necessary for life could become impossible. Some researchers argue that eternal inflation naturally explains this fine-tuning. If countless universes exist with varying properties, then it is not surprising that at least a few possess conditions suitable for life. Intelligent observers would inevitably find themselves in one of the rare universes capable of supporting their existence. In this view, the apparent specialness of our cosmos does not require extraordinary explanation. We observe these conditions because only such conditions allow observers to emerge in the first place. Yet eternal inflation raises profound questions of its own. If new universes are constantly being created, did the larger inflationary process itself have a beginning? Or has it existed forever? Some versions of the theory suggest that inflation could continue infinitely into the future while still requiring an initial starting point. Other models attempt to describe inflation as part of an eternal framework without any true beginning. However, proving either possibility remains extraordinarily difficult. The mathematics becomes increasingly complex when researchers attempt to extend the theory beyond the earliest observable moments. Furthermore, if other universes exist beyond our cosmic horizon, detecting them may be nearly impossible. By definition, these regions are separated from us by distances so vast that light cannot travel between them. This creates a challenge rarely encountered in science. How can a theory be tested if much of what it predicts remains permanently unobservable? Despite these difficulties, eternal inflation remains influential because it emerges naturally from equations developed to explain observable features of our universe. Unlike some speculative ideas, it was not originally invented to address the question of what came before the Big Bang. Instead, it arose as a consequence of attempts to understand the early expansion of space. This gives the theory a degree of scientific credibility that many alternative proposals lack. Researchers continue investigating whether subtle signatures might reveal evidence supporting inflationary models. Patterns in the cosmic microwave background, gravitational waves from the early universe, and other observations may eventually provide important clues. Perhaps the most remarkable aspect of eternal inflation is how dramatically it changes our perspective. For centuries, humanity imagined the universe as the totality of existence. Later we learned that Earth is one planet orbiting one star among billions. Then we discovered that the Milky Way is only one galaxy among countless others. Eternal inflation extends this trend even further. It suggests that our entire observable universe may itself be only one small region within a much greater reality. Every star, every galaxy, every civilization that will ever exist within our cosmic horizon could represent only a tiny fraction of what actually exists. The Big Bang would no longer be the creation of everything. Instead, it would mark the birth of our local cosmic bubble within an endlessly expanding multiverse whose true scale may exceed anything the human mind can fully comprehend. If this vision is correct, then before our Big Bang there may have been not one universe, but an eternal process continuously creating new universes across an infinite sea of space and possibility. While eternal inflation imagines our universe as one bubble among countless others, another extraordinary idea suggests that the Big Bang itself may have been the result of a cosmic bounce. According to this view, our universe was not born from absolute nothingness. Instead, it emerged from the remains of an earlier universe that existed before our own. This concept, often called the Big Bounce, attempts to solve one of the most troubling problems in cosmology, the singularity. In traditional Big Bang models, if we trace the expansion of the universe backward far enough, we eventually arrive at a point where density becomes infinite and the known laws of physics cease to function. Such infinities usually signal that a theory has reached the limits of its usefulness. Physicists generally do not believe that actual infinities exist in nature. Rather, they indicate that our understanding is incomplete. The Big Bounce emerged partly from the desire to avoid this problem. Instead of imagining the universe compressed into an infinitely dense point, some researchers proposed that a previous contracting universe reached an extremely dense state and then rebounded, producing the expansion we observe today. In this picture, the Big Bang was not a beginning but a transition between contraction and expansion. To understand why such a bounce might occur, it helps to consider the forces governing cosmic evolution. Gravity naturally pulls matter together. In a universe filled with matter and energy, gravitational attraction works constantly to slow expansion. For much of the 20th century, many cosmologists expected gravity to eventually halt the growth of the universe and reverse it. Although modern observations suggest that dark energy is currently accelerating expansion, alternative scenarios remain possible under certain conditions. Some theoretical models propose that when matter becomes extraordinarily compressed, quantum effects generate a powerful repulsive force. Instead of allowing density to increase without limit, these effects create a kind of cosmic pressure capable of preventing total collapse. As contraction reaches extreme levels, the repulsive influence becomes dominant, causing the universe to bounce outward once again. Expansion follows contraction just as a compressed spring rebounds after being squeezed. The cycle transforms what would otherwise be a destructive ending into the beginning of a new cosmic era. Several approaches within theoretical physics support versions of this idea. One of the most well-known comes from loop quantum cosmology, a framework attempting to merge quantum mechanics with gravity. In this theory, space is not infinitely divisible. Instead, it possesses a fundamental discrete structure at the smallest scales. Space resembles a woven fabric made from tiny quantum units rather than a perfectly smooth continuum. As a contracting universe becomes increasingly dense, this discrete structure generates quantum effects that resist further compression. Instead of collapsing into a singularity, the universe reaches a minimum size and then begins expanding. The singularity disappears entirely. In its place stands a bridge connecting a previous cosmic phase to our own. If loop quantum cosmology proves correct, then the Big Bang may represent the moment when a prior contracting universe transitioned into the expanding universe we inhabit today. This possibility leads to fascinating questions about the nature of cosmic history. What was the previous universe like? Did it contain galaxies similar to ours? Were there stars illuminating distant skies billions of years before our Big Bang? Could planets have existed around ancient suns? Some researchers speculate that earlier universes may have looked remarkably familiar, governed by laws resembling those we observe today. Others imagine radically different conditions with altered physical constants and unique cosmic structures. It is even possible that countless generations of universes have existed, each giving rise to the next through a sequence of contractions and expansions extending indefinitely into the past. In such a reality, there would be no ultimate beginning. Cosmic history would form an endless chain of transformations, each universe emerging from the remains of its predecessor. An especially intriguing aspect of the Big Bounce concerns information. In ordinary physical processes, information is generally conserved. This principle raises the possibility that traces of a previous universe might survive the bounce and influence the next cosmic cycle. Could subtle patterns in our universe reflect events that occurred before the Big Bang? Some researchers have searched for unusual structures in the cosmic microwave background, the ancient radiation left over from the early universe. Certain speculative studies have suggested that faint signatures might represent echoes from a pre-Big Bang cosmos. These claims remain controversial, and no convincing evidence has yet been accepted by the scientific community. Nevertheless, the idea continues to inspire investigation. If information can cross the boundary between cosmic cycles, then the universe may preserve a hidden memory of events that occurred long before the stars and galaxies we know today came into existence. The philosophical implications are equally profound. The Big Bounce challenges the traditional image of creation as a singular event. Instead of asking how something emerged from nothing, we ask how one state of existence transformed into another. Reality becomes a continuous process rather than a sudden appearance. Time may extend beyond the Big Bang into earlier epochs, allowing cosmic history to stretch far deeper into the past than previously imagined. This perspective aligns with a recurring theme in science. Boundaries once believed absolute often turn out to be transitions connecting larger structures. The surface of Earth is not the edge of reality but part of a planet. The horizon is not the end of the world but merely the limit of sight. Perhaps the Big Bang itself belongs to the same category. What appears to be a beginning may ultimately prove to be a doorway connecting different phases of an eternal cosmos. Of course, significant challenges remain. No current theory of quantum gravity has been experimentally confirmed. The extreme conditions associated with a cosmic bounce are far beyond the reach of present-day laboratories. Much of the evidence remains indirect and theoretical. Future observations may support, modify, or entirely reject these ideas. Yet the Big Bounce remains one of the most compelling alternatives to traditional origin stories because it replaces a mysterious singularity with a physically meaningful process. Instead of confronting an impenetrable wall where explanation ends, it offers a bridge leading into a deeper cosmic past. If this vision is correct, then before the Big Bang there may have been another universe growing older beneath different constellations, filled with its own galaxies, stars, and histories. Its final collapse would not have been the end of existence but the event that ultimately gave birth to the universe we call home. Among the most mysterious ideas ever proposed in cosmology is the possibility that time itself did not exist before the Big Bang. This concept is difficult to grasp because every aspect of human experience depends upon time. We think in terms of before and after. We remember the past, act in the present, and imagine the future. Every story ever told unfolds through a sequence of events. Even our language is built around temporal relationships. Because of this, it feels natural to ask what happened before the universe began. Yet some physicists argue that the question may be fundamentally mistaken. If time originated with the Big Bang, then there was no earlier moment in which something could happen. In this view, asking what came before the Big Bang is similar to asking what lies south of the South Pole or what is beyond the edge of a sphere. The question assumes the existence of a direction that simply does not exist. This possibility emerged not from philosophy alone but from serious attempts to understand the mathematics of space-time. According to Einstein's theory of general relativity, space and time are not separate entities. Together they form a unified structure known as space-time. Matter and energy influence this structure, causing it to bend, stretch, and evolve. When cosmologists trace the expansion of the universe backward, space-time itself shrinks toward the earliest moments. The Big Bang is not merely the beginning of matter and energy. It may represent the beginning of space-time itself. To appreciate how radical this idea is, imagine watching a film. Every scene appears in sequence because the film contains a timeline. Now imagine asking what happened before the first frame of the movie. Within the story itself, there is no answer because the timeline begins with that frame. Something similar may apply to the universe. Time could be a feature that emerged alongside the cosmos rather than a pre-existing stage upon which cosmic events occurred. If this is true, then the universe did not appear within time. Instead, time appeared with the universe. The distinction may seem subtle at first, but it completely transforms how we think about origins. In everyday life, every event has a cause that precedes it. A seed grows into a tree. A spark ignites a fire. A person opens a door because they first decide to do so. Causes come before effects. Yet causality itself depends upon time. If time begins at the Big Bang, then asking what caused the Big Bang becomes problematic because causation requires temporal order. Without time, concepts such as before, after, cause, and effect may lose their ordinary meanings. Some of the most influential work on this subject came from attempts to combine cosmology with quantum mechanics. Physicists discovered that under certain conditions, time behaves very differently than our everyday intuition suggests. One famous proposal introduced the concept of imaginary time, a mathematical framework in which the distinction between space and time becomes less clear. In this model, the earliest universe resembles a smooth geometric shape without a boundary. Just as the surface of Earth has no edge, space-time might have no true beginning. Traveling far enough toward the past would not bring you to a starting point but to a region where conventional notions of time gradually dissolve. This idea became known as the no-boundary proposal. According to this picture, the universe does not require a singular moment of creation because there is no sharp boundary separating existence from non-existence. The beginning becomes more like a transition than an event. The implications are profound. If the universe has no boundary in time, then the search for a prior cause may be unnecessary. The cosmos simply exists as a self-contained structure. Many people find this deeply unsatisfying because human intuition naturally seeks explanations. We want to know why something exists rather than nothing. We expect every event to have a cause. Yet nature repeatedly challenges these assumptions. Quantum mechanics already describes processes that appear fundamentally probabilistic. Certain events occur without deterministic causes in the classical sense. If reality behaves this way at its deepest levels, then perhaps the demand for a prior cause of the universe reflects human intuition rather than physical necessity. The cosmos may not need an external explanation in the way we imagine. At the same time, other physicists remain cautious. They argue that the apparent beginning of time may reflect limitations in our current theories rather than an ultimate truth. Just as previous generations believed certain mysteries were impossible to solve, future advances in physics may reveal deeper structures extending beyond the Big Bang. What appears to be the beginning of time could eventually prove to be a transition into another temporal regime. New theories of quantum gravity might uncover hidden dimensions or pre-existing states where time behaves differently from anything we currently understand. The history of science contains many examples where boundaries once considered fundamental later disappeared. Therefore, some researchers hesitate to accept the idea that time truly began at the Big Bang until stronger evidence becomes available. Nevertheless, the possibility remains one of the most intellectually challenging ideas in modern cosmology. It forces us to question assumptions so deeply embedded in our thinking that we rarely notice them. We tend to imagine time as a universal backdrop stretching infinitely in both directions. Yet physics increasingly suggests that time may be more fragile, more dynamic, and more mysterious than previously believed. It may emerge under certain conditions and disappear under others. In the extreme environment of the early universe, distinctions that seem obvious in everyday life may lose their meaning entirely. Past and future, cause and effect, beginning and ending could all become concepts applicable only within certain regions of reality. Perhaps the greatest lesson of this idea is humility. Human beings evolved to navigate ordinary environments, not the earliest moments of cosmic history. Our intuitions were shaped by daily experiences involving clocks, seasons, aging, and motion. There is no reason to expect those intuitions to remain reliable when applied to the birth of space-time itself. The universe has repeatedly revealed that reality operates in ways far stranger than common sense would predict. If time truly began with the Big Bang, then the mystery of what came before may have no answer because there was no before. The cosmos would not emerge from an earlier state but from the very origin of temporal existence itself. In that case, the Big Bang would represent not merely the birth of the universe but the birth of history, causality, and every moment that has ever existed or ever will exist. If the idea that time began with the Big Bang seems difficult to accept, an even stranger possibility awaits. Some physicists have proposed that our universe may have originated inside a black hole that exists within another universe. At first glance, this sounds like science fiction. Black holes are usually imagined as cosmic traps, regions where gravity becomes so powerful that nothing can escape once it crosses a boundary known as the event horizon. Stars, planets, gas, light, and even information appear to vanish into these mysterious objects. Yet as researchers explored the mathematics of black holes more deeply, they discovered surprising similarities between black holes and the Big Bang itself. Both involve extreme densities. Both push the known laws of physics to their limits. Both contain regions where our current understanding breaks down. These similarities led some theorists to wonder whether black holes and universes might be connected in ways far more profound than anyone had previously imagined. To understand this possibility, imagine a massive star reaching the end of its life. For millions of years, nuclear reactions inside the star balance the inward pull of gravity. Eventually the fuel is exhausted. Without enough outward pressure, gravity begins crushing the star inward. The collapse accelerates dramatically. In certain cases, the star becomes so compressed that a black hole forms. From the perspective of an outside observer, the black hole appears as a dark sphere surrounded by an invisible event horizon. Anything crossing this boundary can no longer communicate with the outside universe. The interior becomes hidden from view. According to traditional interpretations of general relativity, matter falling into a black hole continues collapsing until it reaches a singularity, a point of infinite density where known physics ceases to function. However, many physicists suspect that singularities are not real physical objects. Instead, they may indicate that our theories are incomplete. If quantum effects prevent true singularities from forming, then something very different might occur deep within a black hole. This is where the idea becomes truly fascinating. Some theoretical models suggest that instead of ending in a singularity, collapsing matter could create a new expanding region of space-time. From the perspective of observers inside that region, it would resemble a Big Bang. A new universe would begin expanding, developing its own space, time, stars, galaxies, and cosmic history. Meanwhile, from the perspective of the parent universe, the process would simply appear as the formation of a black hole. In this scenario, every black hole could potentially contain an entire universe hidden beyond the event horizon. Our own universe might therefore be the interior of a black hole that formed within a much older and larger cosmos. The Big Bang would not represent the ultimate beginning of existence. It would mark the moment when our region of spacetime emerged from gravitational collapse occurring elsewhere. This concept offers an intriguing answer to one of cosmology's most difficult questions. Rather than asking how a universe appeared from nothing, it proposes that universes are born naturally through processes already known to occur throughout the cosmos. Black holes become cosmic seeds. Each new universe arises from the collapse of matter in a previous one. Reality becomes a vast generational structure in which universes give birth to other universes across unimaginable spans of time. Just as stars produce heavier elements that eventually form planets and life, universes themselves could participate in an ongoing cycle of cosmic reproduction. Some physicists have even suggested that this process might resemble a kind of natural selection. Universes producing large numbers of black holes would generate more offspring universes. Over immense periods, certain physical laws might become more common because they favor black hole formation. Although highly speculative, this idea attempts to explain why our universe possesses the particular properties we observe. The image that emerges is extraordinary. Imagine a vast cosmic family tree extending across dimensions beyond human perception. Each universe contains billions of galaxies. Within those galaxies, countless stars eventually die and form black holes. Some of those black holes become the birthplaces of new universes. Those universes later generate black holes of their own, producing further generations. Reality expands not only through space but through an endless hierarchy of nested cosmic worlds. Every universe carries within it the potential to create others. The observable cosmos becomes one branch in an immense structure whose true scale may be impossible to comprehend. Of course, enormous challenges confront this hypothesis. The interiors of black holes remain inaccessible to direct observation. By definition, information cannot easily escape from beyond an event horizon. Testing such ideas therefore becomes extremely difficult. Researchers must rely on mathematical consistency and indirect evidence rather than direct measurement. Furthermore, no complete theory currently unites quantum mechanics and gravity in a way capable of describing black hole interiors with certainty. Until such a theory is developed, many aspects of these models remain speculative. Nevertheless, the concept continues attracting interest because it connects two of the greatest mysteries in physics, black holes and cosmic origins. Instead of treating them as separate phenomena, it suggests they may be different aspects of the same deeper process. There is also a philosophical beauty to this picture. Human beings often search for absolute beginnings, singular moments when everything suddenly appeared. Yet nature repeatedly reveals networks, cycles, and relationships rather than isolated events. Forests emerge from seeds produced by earlier trees. Rivers flow through landscapes shaped by older geological processes. Stars form from material created by previous generations of stars. The black hole universe hypothesis extends this pattern to the largest scales imaginable. Our universe would not stand alone. It would be connected to a lineage stretching beyond the observable limits of space and time. The Big Bang would become not a solitary act of creation but one chapter in an ongoing cosmic story. Whether this vision reflects reality remains unknown. Future advances in quantum gravity, black hole physics, and cosmology may support or disprove these ideas. Yet the possibility remains captivating because it transforms our understanding of origins. If our universe was born inside a black hole, then before the Big Bang there may have been another universe filled with its own galaxies, stars, and civilizations. Somewhere within that ancient cosmos, a massive star may have collapsed, creating a black hole. Beyond its event horizon, a new space-time region began expanding. Billions of years later, that expanding region would become the universe we inhabit today. In this extraordinary scenario, every star in our night sky would ultimately owe its existence to a black hole in a parent universe whose existence we can barely imagine. As scientists searched for clues about what might have existed before the Big Bang, some began to question one of the most basic assumptions in cosmology, the idea that our universe is all that exists. This led to the development of one of the most controversial and fascinating concepts in modern science, the multiverse. Unlike earlier theories that attempt to describe a single cosmic history extending beyond the Big Bang, the multiverse suggests that reality may contain an enormous number of universes existing simultaneously. Our universe would not be the entirety of existence but only one region within a far larger structure. In this framework, the question of what came before the Big Bang becomes more complicated because the Big Bang may represent only the local beginning of our universe, not the origin of reality itself. Just as the birth of a single star does not mark the birth of the entire galaxy, the birth of our cosmos may not mark the beginning of all existence. The roots of the multiverse idea arise from several independent areas of physics. One source comes from eternal inflation, where new universes continuously form as inflation ends in different regions of space. Another comes from quantum mechanics, particularly interpretations suggesting that every possible outcome of a quantum event may actually occur in separate branches of reality. Yet another originates from string theory, a mathematical framework proposing that fundamental particles are tiny vibrating strings existing within higher dimensional spaces. Surprisingly, these very different approaches often point toward the same conclusion: reality may be much larger than the observable universe. Instead of one cosmos, there may be countless universes, each governed by its own conditions, structures, and histories. Imagine standing on a beach and examining a single grain of sand. To the grain itself, it might seem unique and isolated. Yet from a broader perspective, it is merely one particle among billions. The multiverse hypothesis suggests that our universe could occupy a similar position within a much greater reality. Every galaxy we observe, every star that has ever shone, every civilization that has ever existed could represent only a tiny fraction of existence as a whole. Beyond our cosmic horizon may lie universes completely inaccessible to us. Some may resemble our own closely. Others could differ so dramatically that familiar matter, chemistry, and even space itself behave in unfamiliar ways. One of the most intriguing motivations for the multiverse comes from the apparent fine-tuning of physical constants. The laws of nature appear balanced with extraordinary precision. Gravity is strong enough to form stars but not so strong that the universe collapses immediately. Electromagnetic forces allow atoms to exist. Nuclear reactions inside stars create heavier elements necessary for planets and life. Small changes in these constants could render the universe sterile and lifeless. For decades, physicists struggled to understand why reality appears so delicately arranged. The multiverse offers a possible answer. If countless universes exist with different physical properties, then most would be unsuitable for life. Intelligent observers would naturally find themselves in one of the rare universes where conditions permit their existence. In this view, the apparent specialness of our universe does not require a unique explanation. It reflects a selection effect. We observe a life-friendly universe because only such universes contain observers capable of asking the question. This idea can feel unsettling because it challenges humanity's desire for uniqueness. Throughout history, scientific discoveries repeatedly displaced humanity from central positions. Earth was not the center of the cosmos. The Sun was not unique. The Milky Way turned out to be one galaxy among billions. The multiverse extends this trend further than ever before. Even our entire universe may not occupy a privileged position. We may inhabit one cosmic bubble among an unimaginable number of others. To some scientists, this is a natural continuation of previous discoveries. To others, it raises concerns because many proposed universes remain forever beyond observation. If something can never be detected, can it truly be considered scientific? This question lies at the heart of ongoing debate surrounding the multiverse. Despite the controversy, the concept has generated extensive research. Cosmologists have explored whether collisions between neighboring universes might leave subtle imprints in the cosmic microwave background. Others investigate whether mathematical patterns within fundamental physics indirectly support multiverse scenarios. So far, no definitive evidence has emerged. Yet neither has the idea been ruled out. As theoretical models become more sophisticated, researchers continue searching for ways to test predictions associated with multiple universes. The challenge is immense because the scales involved exceed anything humans can directly observe. Beyond its scientific implications, the multiverse transforms how we think about possibility itself. If an enormous number of universes exist, then almost every physically allowed scenario may occur somewhere. There could be universes where stars form differently, where galaxies never emerge, where time flows in unfamiliar ways, or where entirely different forms of complexity arise. Some may be nearly identical to our own except for tiny differences. Others may be so alien that human language struggles to describe them. Reality becomes a vast landscape of possibilities rather than a single unfolding story. When viewed through this lens, the Big Bang takes on a new meaning. Instead of representing the creation of all existence, it becomes the birth of our particular universe within a much larger cosmic environment. The question, what came before the Big Bang, no longer demands a single answer. The Big Bang may have occurred within an already existing multiverse, emerging as one event among countless others. Before our cosmic beginning, other universes may have existed, expanded, evolved, and perhaps even disappeared. Entire histories may have unfolded beyond our horizon while our own universe had not yet come into being. Whether the multiverse ultimately proves correct remains one of the great unanswered questions of modern science. Yet its importance lies not only in its potential accuracy but also in the way it expands our imagination. It reminds us that reality may be far larger than the portion we can see. The observable universe, immense as it appears, might represent only a small fragment of a deeper and more complex existence. If that is true, then before our Big Bang there may have been countless other universes already shining with their own stars, forming their own galaxies, and experiencing their own cosmic histories long before our first atom came into existence. As extraordinary as the multiverse may seem, some physicists have ventured even further, proposing that the deepest level of reality is not made of matter, energy, space, or even time. Instead, they suggest that mathematics itself may be the fundamental substance of existence. At first glance, this sounds more like philosophy than science. After all, mathematics is usually thought of as a language invented by humans to describe patterns in nature. Numbers, equations, and geometric shapes appear to exist only in books, computers, or human minds. Yet the success of mathematics in physics has long puzzled scientists. Again and again, abstract mathematical structures developed without any connection to reality later turned out to describe the universe with astonishing accuracy. Equations written on paper often predict phenomena decades before they are observed. The motion of planets, the behavior of atoms, the existence of black holes, and even the expansion of the universe were all revealed through mathematics before direct evidence confirmed them. This remarkable effectiveness has led some thinkers to ask a profound question: what if mathematics is not merely describing reality? What if reality itself is mathematical? The idea gained attention because the laws governing the universe appear deeply mathematical. Every physical process can be represented through equations. Gravity follows precise geometric relationships. Quantum particles obey mathematical probabilities. Light, energy, and motion all conform to structures that can be expressed through symbols and formulas. The deeper scientists investigate nature, the more mathematical it appears. Some researchers argue that this is not a coincidence. They suggest that physical reality and mathematical reality may actually be the same thing. According to this view, the universe exists because certain mathematical structures exist. Space, time, matter, and energy are not fundamental entities. They emerge from deeper mathematical relationships. If this perspective is correct, then asking what came before the Big Bang may require abandoning many familiar concepts. The answer may not involve another universe, another dimension, or a prior moment in time. Instead, it may involve timeless mathematical structures existing independently of physical reality. This notion leads to a fascinating possibility. Mathematical objects do not appear to require creation. The number 2 does not come into existence and then disappear. Geometric truths remain valid regardless of whether anyone observes them. The relationship between the angles of a triangle exists independently of stars, galaxies, or human civilizations. If reality is fundamentally mathematical, then perhaps the universe does not need a cause in the conventional sense. It exists because certain mathematical structures are logically possible. The Big Bang would then represent the emergence of one particular mathematical reality into a physical form. Our universe becomes an expression of deeper abstract principles rather than a product of material processes occurring beforehand. Some versions of this idea go even further. They propose that every mathematically consistent structure exists as its own universe. In such a framework, reality becomes unimaginably vast. Every possible set of mathematical laws corresponds to a different universe. Some resemble our own closely. Others operate according to entirely different principles. There may be universes with more dimensions, fewer dimensions, different forces, or radically different forms of logic. The cosmos becomes not merely a collection of physical worlds but a landscape of mathematical possibilities. Our universe exists because it is one of the mathematical structures capable of supporting complex patterns, stars, galaxies, and conscious observers. The implications are both exciting and unsettling. On one hand, this perspective offers a potential explanation for why the universe follows orderly laws. The laws are not imposed externally. They arise naturally from the mathematical structure underlying reality. On the other hand, the idea challenges deeply held assumptions about existence. Most people think of mathematics as something discovered by intelligent minds. If mathematics itself forms the foundation of reality, then the relationship between mind and universe becomes much more mysterious. Did mathematics exist before the universe? If so, where did it exist? Can abstract structures truly be said to exist independently of physical objects? These questions blur the distinction between physics, philosophy, and metaphysics. Critics point out that the mathematical universe hypothesis faces significant challenges. Although mathematics describes nature with extraordinary precision, describing something is not necessarily the same as being that thing. A map can accurately represent a city without literally becoming the city. Likewise, equations may model reality without constituting reality itself. Furthermore, proving that mathematics exists independently of minds remains difficult. The debate continues among philosophers and scientists alike. Nevertheless, the idea remains influential because it addresses questions that traditional physical explanations struggle to answer. If the universe ultimately rests upon mathematical foundations, then origins may not require a physical cause at all. Another intriguing consequence concerns time. Mathematical structures are timeless. A theorem does not age. A geometric relationship does not evolve. It simply exists. If reality emerges from such structures, then the distinction between past, present, and future may be less fundamental than it appears. Some physicists already suspect that time is not a basic feature of the universe but an emergent phenomenon arising from deeper laws. The mathematical universe concept aligns naturally with this possibility. The Big Bang would no longer represent the first moment in time. Instead, it would be the point at which temporal experience emerges within a timeless mathematical framework. From this perspective, the search for what came before the Big Bang may resemble asking what existed before a mathematical truth. The question itself may be misplaced because the underlying structure does not occupy time. It simply exists. The universe unfolds according to its internal relationships, generating stars, galaxies, planets, and conscious beings capable of reflecting upon their origins. What we perceive as cosmic history becomes a feature of the structure rather than evidence of a prior cause. Whether this vision reflects reality remains uncertain. Future discoveries may reveal entirely different explanations for cosmic origins. Yet the mathematical universe hypothesis demonstrates how radically our understanding of existence can evolve when we push beyond familiar assumptions. It reminds us that the deepest answers may not involve objects, places, or events at all. They may involve principles so abstract that ordinary language struggles to capture them. If this idea is correct, then before the Big Bang there may have been no matter, no energy, no stars, and no time. There may have existed only timeless mathematical possibilities, one of which eventually gave rise to the universe we now call home. While some theories suggest that the universe emerged from mathematics, quantum fluctuations, or previous cosmic cycles, another possibility is even more unsettling. What if reality itself is far more artificial than we imagine? What if the universe did not arise naturally at all? This question has led some thinkers to explore the simulation hypothesis, the idea that our universe may be a constructed reality generated by an intelligence existing beyond the limits of our observable cosmos. Although this concept is often associated with science fiction, it has attracted serious philosophical discussion because of certain trends in technology and physics. As human civilizations become increasingly capable of creating virtual worlds, some researchers have wondered whether sufficiently advanced beings might eventually simulate entire universes, complete with stars, galaxies, planets, and conscious inhabitants. If such simulations are possible, then the number of simulated realities could vastly exceed the number of original physical universes. Statistically, some argue, it might become more likely that observers find themselves inside a simulation rather than in a base-level reality. At first, the idea sounds almost absurd. The universe appears far too large and complex to be artificial. The observable cosmos contains hundreds of billions of galaxies. Each galaxy contains billions of stars. The distances involved are almost beyond comprehension. Light requires years to cross the space between stars and millions of years to travel between galaxies. Yet modern computing offers an interesting perspective. Virtual worlds do not necessarily need to calculate every detail at every moment. Many computer simulations only render information when it becomes necessary. Details outside the observer's view may remain undefined until observation occurs. Some people have pointed out that quantum mechanics occasionally seems to behave in surprisingly similar ways. Subatomic particles often exist in states of probability until measurements occur. While this does not prove anything about simulations, it demonstrates why the idea continues attracting curiosity. The simulation hypothesis becomes especially relevant when discussing what came before the Big Bang. If the universe is artificial, then the Big Bang might represent the initialization of a system rather than a natural cosmic origin. Imagine turning on a computer simulation. From the perspective of the characters inside the program, time begins at the moment the simulation starts. They would perceive a universe suddenly appearing, complete with physical laws and an unfolding history. Yet outside the simulation, another reality already exists. The beginning observed by the simulated inhabitants would not be the beginning of everything. It would merely be the beginning of their particular environment. In this scenario, asking what came before the Big Bang is similar to asking what existed before a computer program was launched. The answer lies outside the universe rather than within it. This possibility raises fascinating questions. Who or what created the simulation? Why was it created? Could it be an experiment, a historical reconstruction, a scientific investigation, or something beyond human imagination? If an external intelligence exists, its nature might be impossible for us to comprehend. It could belong to a civilization billions of years older than our own. It might possess technological capabilities so advanced that they appear indistinguishable from magic. Entire galaxies could be simulated with ease. Conscious beings could emerge naturally within artificial environments without ever realizing their true situation. Supporters of the simulation hypothesis often point to the rapid advancement of computing technology. Only a few decades ago, digital worlds consisted of simple shapes and primitive graphics. Today, computers can generate environments of remarkable complexity. Artificial intelligence creates realistic conversations, images, and behaviors. Virtual reality increasingly blurs the distinction between physical and digital experiences. If technological progress continues for centuries or millennia, future civilizations may develop simulations of extraordinary sophistication. They might recreate entire planets, ecosystems, or even universes. If this becomes possible, the number of simulated realities could eventually become enormous. Some philosophers argue that under such circumstances, it may be statistically reasonable to suspect that we inhabit one of them. However, enormous challenges accompany this idea. There is currently no direct evidence that our universe is a simulation. Many proposed tests remain speculative and controversial. Some researchers have suggested searching for computational limits within physical laws, such as minimum scales of space or unusual patterns in cosmic rays. Others examine whether the universe displays signs of optimization similar to those used in computer systems. So far, none of these investigations have produced convincing proof. Most scientists remain skeptical, viewing the simulation hypothesis as an interesting philosophical possibility rather than an established scientific theory. Yet the concept remains valuable because it forces us to reconsider assumptions about reality. Throughout history, humanity repeatedly discovered that appearances can be misleading. Earth seemed stationary but was moving through space. Solid matter appeared continuous but was composed of atoms. Space and time seemed absolute but turned out to be flexible. The simulation hypothesis extends this tradition of questioning the obvious. It asks whether the reality we experience directly is truly fundamental or merely part of a deeper structure beyond our perception. There is also a curious connection between this idea and ancient philosophical traditions. Long before computers existed, thinkers wondered whether reality might be an illusion. Philosophers questioned whether sensory experiences accurately reflected the true nature of existence. Some argued that the world perceived by human beings was only a shadow of a deeper reality. Modern simulation arguments echo these ancient concerns in a technological form. The language has changed, but the underlying mystery remains surprisingly familiar. If the simulation hypothesis were correct, then the answer to what came before the Big Bang would be radically different from most cosmological theories. Before our universe began, another level of reality already existed. The Big Bang would mark the activation of our cosmic system rather than the birth of existence itself. Beyond the limits of our observable universe might lie a realm governed by entirely different laws, inhabited by entities whose understanding of reality exceeds ours as dramatically as our understanding exceeds that of primitive organisms. Whether this possibility is true remains unknown. Yet it illustrates how the search for origins can lead us into territories where science, philosophy, and imagination become almost impossible to separate. In confronting the mystery of what came before the Big Bang, humanity finds itself exploring not only the boundaries of the universe but also the boundaries of its own understanding. As we journey deeper into the mystery of what came before the Big Bang, we encounter an idea that challenges perhaps the most basic assumption of all, the belief that the laws of physics have always been the same. Most people naturally imagine that gravity, light, matter, and time operate according to eternal rules. We assume the laws governing the universe today also governed the universe yesterday, billions of years ago, and perhaps forever. Yet some physicists have suggested a startling alternative. What if the laws of nature themselves evolved? What if the physical rules shaping our universe emerged from a more primitive reality where no stable laws yet existed? In such a scenario, the Big Bang would not simply mark the birth of matter and energy. It would also represent the birth of the very rules that make reality understandable. To appreciate the significance of this possibility, consider how dependent the universe is on its physical laws. Every star shines because nuclear forces operate with precise strengths. Every planet follows predictable orbits because gravity behaves consistently. Every atom exists because electromagnetic interactions possess particular values. Even tiny changes to these laws could produce a dramatically different cosmos. If gravity were slightly stronger, stars might burn too quickly. If it were weaker, galaxies might never form. The universe appears astonishingly ordered, almost as though it follows a carefully written script. Yet this observation leads to a difficult question. Why do these laws exist in their present form? Why are the constants of nature exactly what they are and not something else? Traditional physics usually treats these laws as fixed features of reality. They simply exist. However, some researchers have explored the possibility that laws themselves may be products of cosmic evolution. According to certain theoretical models, the earliest state of existence may have been far more chaotic than anything we can imagine. Instead of stable particles, predictable forces, and orderly space-time, there may have been a turbulent realm where physical properties fluctuated wildly. No permanent structure existed. No galaxies could form. No atoms could survive. Reality was a shifting ocean of possibilities. Over immense periods, or perhaps through processes beyond conventional time, stable laws gradually emerged. The universe we inhabit today would then be the result of a kind of cosmic selection process favoring order over chaos. This concept bears a surprising resemblance to biological evolution. On Earth, countless forms of life appeared throughout history, but only certain organisms successfully adapted and survived. Natural selection gradually produced the complex ecosystems we observe today. Some physicists have wondered whether a similar principle could operate on cosmic scales. Perhaps many possible sets of physical laws exist, but only a small number produce stable universes capable of long-term development. Universes governed by unsuitable laws would quickly collapse or remain chaotic and lifeless. Those with favorable conditions would endure, forming stars, planets, and eventually observers capable of studying their surroundings. In this view, the laws of nature are not timeless absolutes. They are survivors in a vast landscape of possibilities. One particularly intriguing proposal comes from theories involving cosmic natural selection. According to this idea, universes capable of producing large numbers of black holes may generate offspring universes through processes occurring inside those black holes. Each new universe inherits physical laws similar to its parent but with slight variations. Over many generations, universes that excel at producing black holes become increasingly common. The laws of nature evolve much like genetic traits evolve within biological populations. While highly speculative, this framework offers a fascinating explanation for why our universe appears finely tuned. Its properties may not be arbitrary. They may result from an immense evolutionary history extending far beyond the observable cosmos. Another possibility suggests that physical laws emerge from deeper mathematical structures. In this view, what we call laws are not fundamental realities but effective descriptions arising under particular conditions. Just as temperature emerges from the motion of countless molecules, gravity and spacetime might emerge from deeper processes operating beneath observable reality. Before the Big Bang, those processes may have existed in forms radically different from anything familiar. Stable laws had not yet crystallized. The universe existed in a state where the distinction between different forces, dimensions, and particles had not yet emerged. As the cosmos expanded and cooled, recognizable laws gradually appeared, shaping the universe into the ordered structure we see today. The implications are profound. If physical laws can evolve, then the universe may be far more dynamic than previously imagined. Reality becomes not merely a stage upon which events occur but an evolving system capable of generating its own rules. The Big Bang transforms from a simple beginning into a phase transition during which order emerged from a more fundamental chaos. Before that transition, concepts we take for granted may have been meaningless. Gravity might not have existed in its current form. Time may have behaved differently or not existed at all. Even mathematics could have manifested through unfamiliar structures beyond human comprehension. Of course, these ideas remain speculative. Testing them presents enormous challenges because they concern conditions beyond the reach of direct observation. Yet they continue attracting attention because they address questions traditional cosmology often leaves unanswered. Instead of accepting physical laws as unexplained givens, they seek deeper explanations for why those laws exist and why they possess their particular forms. This ambition reflects one of the defining characteristics of science, the refusal to stop questioning. There is also something deeply humbling about this perspective. Human beings often assume that the universe we observe represents reality in its final form. We study galaxies, stars, atoms, and particles, believing we are uncovering the ultimate structure of existence. Yet history repeatedly teaches otherwise. Every era believed it had reached the foundation of knowledge, only to discover deeper layers hidden beneath. The notion that physical laws themselves might emerge from more fundamental processes continues this tradition. It suggests that our current understanding may be only one step in a much longer journey. If this idea is correct, then before the Big Bang there may not have been a universe governed by familiar laws. There may have existed a primordial realm of possibilities where the rules of reality had not yet settled into stable forms. The forces shaping our cosmos today would eventually emerge from that deeper state, much as crystals form within cooling liquid. The Big Bang would mark the moment when order crystallized from cosmic chaos, giving rise not only to matter and energy but to the very laws that allow the universe to exist as a coherent and comprehensible whole. Among the most ambitious ideas ever developed in theoretical physics is the possibility that our universe is only a tiny part of a much larger multidimensional reality. According to this view, the familiar 3 dimensions of space and 1 dimension of time may not represent the full structure of existence. Hidden beyond everyday perception could be additional dimensions folded into the fabric of reality itself. These dimensions might be incredibly small, inaccessible to ordinary observation, or they might extend across scales far greater than the observable universe. If such dimensions exist, then the mystery of what came before the Big Bang may require looking beyond the universe entirely and into a higher dimensional realm where our cosmos is only one component of a far larger structure. The idea of extra dimensions emerged from attempts to unify the forces of nature. Physicists have long sought a theory capable of explaining gravity, electromagnetism, and the nuclear forces within a single framework. During this search, researchers discovered that certain mathematical models work more naturally when additional dimensions are included. In theories such as string theory, the universe may contain 10, 11, or even more dimensions. While most remain hidden from direct observation, they could profoundly influence the behavior of reality. Particles, forces, and space-time itself may be manifestations of deeper multidimensional structures. What appears simple from our perspective could be only a small projection of a vastly more complex reality. To understand this concept, imagine a 2-dimensional creature living on a flat sheet of paper. Such a being would know only length and width. The idea of height would be almost impossible to comprehend because it lies beyond direct experience. Yet a 3-dimensional observer could see the entire sheet from above and interact with it in ways the flat creature could never imagine. Some physicists suggest that humanity may occupy a similar position. We experience only a limited subset of dimensions while larger aspects of reality remain hidden. Events occurring in higher dimensional space could influence our universe even if we cannot directly perceive them. This possibility becomes especially intriguing when applied to the origin of the cosmos. Certain theories propose that our universe exists on a vast 3-dimensional membrane, often called a brane, floating within a higher dimensional space sometimes referred to as the bulk. Multiple brands may coexist within this larger environment. For immense periods, they drift through higher dimensional space. Eventually, 2 brands collide. The collision releases enormous amounts of energy, producing conditions remarkably similar to those associated with the Big Bang. In this scenario, the Big Bang is not the beginning of existence. It is the result of an interaction occurring within a pre-existing multidimensional reality. Before our universe emerged, the higher dimensional bulk already existed, along with other brands moving through it. The image created by this theory is extraordinary. Instead of imagining the universe as all of existence, we picture it as a surface suspended within a larger cosmic ocean. Galaxies, stars, planets, and every form of matter occupy only one layer of a far deeper structure. Beyond our universe may lie other brands containing their own universes, each with unique histories and physical properties. Entire cosmic civilizations could exist on neighboring brands without any possibility of direct contact. Their stars would shine in inaccessible dimensions. Their histories would unfold beyond our perception. The bulk becomes a hidden realm connecting countless universes while remaining largely invisible to those living within them. One reason physicists find these ideas attractive is that they may help solve difficult cosmological problems. For example, some versions naturally explain why gravity appears much weaker than the other fundamental forces. Gravity may spread through additional dimensions while the other forces remain confined to our brain. This would make gravity seem unusually weak from our perspective even though its true influence extends far beyond the observable universe. Similarly, multidimensional models offer new ways of understanding cosmic expansion, dark matter, and the earliest moments of cosmic history. The possibility of higher dimensions also changes how we think about time. In ordinary experience, time flows relentlessly forward. Yet within certain multidimensional frameworks, time may be only one aspect of a larger structure. Other dimensions could contain relationships that transcend familiar temporal order. Events appearing separated by billions of years within our universe might correspond to simple geometric relationships within higher dimensional space. The Big Bang would then become not merely a historical event but a feature of a broader multidimensional landscape. Of course, these ideas remain highly speculative. No direct evidence for extra dimensions has yet been discovered. Experiments conducted in particle accelerators have searched for signs of hidden dimensions but have not produced definitive results. Astronomers continue investigating whether subtle gravitational effects or unusual cosmological observations might reveal the influence of higher dimensional structures. The challenge is immense because these dimensions may operate at scales far beyond current technology. Yet the absence of evidence has not eliminated the possibility. Many physicists continue exploring these models because they offer elegant mathematical solutions to problems that remain difficult to explain otherwise. There is also a profound philosophical aspect to this vision. Throughout history, humanity repeatedly discovered that reality extends beyond what the senses reveal. The Earth is not flat. The sky is not a solid dome. The Milky Way is not the entire universe. Every expansion of knowledge revealed larger structures hidden behind familiar appearances. The concept of higher dimensions continues this trend on an even grander scale. It suggests that the universe itself may not be the ultimate level of reality. Instead, it could be one component within a vast multidimensional architecture whose true scale exceeds ordinary imagination. If this perspective proves correct, then before the Big Bang there may have been no singularity, no absolute beginning, and no creation from nothing. There may have existed an ancient multidimensional realm where enormous cosmic structures drifted through hidden dimensions. The event we call the Big Bang would simply be the moment when those structures interacted, releasing energy and creating the universe we inhabit today. Beyond our cosmic horizon, beyond space and time as we understand them, that greater reality may still exist, silently shaping the cosmos while remaining forever beyond the reach of direct observation. In that case, the mystery of what came before the Big Bang would lead not to an empty void but to an immense multidimensional universe far older and far larger than anything humanity has yet imagined. Theories about higher dimensions, multiverse, and cosmic cycles grew increasingly sophisticated. Some physicists began asking an even more radical question. What if the universe did not emerge from something else at all? What if the deepest mystery is not how the universe began, but why there is existence instead of absolute nothingness? At first glance, the distinction may seem subtle. Yet it lies at the heart of one of the oldest and most profound questions ever asked. Every theory we have explored so far assumes that some form of reality already exists. There may be a quantum vacuum, a previous universe, a higher dimensional space, a mathematical structure, or an eternal multiverse. But each explanation leaves one question unanswered: why does that underlying reality exist in the first place? If we continue tracing causes backward, eventually we seem to arrive at a final mystery that refuses to disappear. Why is there something rather than nothing? The challenge begins with the concept of nothing itself. Most people imagine nothingness as an empty void, a vast black space devoid of stars, planets, and matter. Yet from a scientific perspective, empty space is not truly nothing. Even the vacuum contains quantum fields, fluctuating energy, and physical laws. A completely empty universe still possesses space-time. It still has structure. It still exists. True nothingness would be far more extreme. There would be no space, no time, no energy, no particles, no dimensions, no laws of physics, and no possibility of events occurring. It is difficult even to describe such a state because language itself assumes the existence of things. The moment we imagine a dark void, we have already introduced space. The moment we imagine duration, we have introduced time. Genuine nothingness appears almost impossible for the human mind to conceive. This difficulty has led some philosophers and physicists to wonder whether absolute nothingness is actually impossible. Perhaps existence is not something that requires explanation. Perhaps non-existence is the condition that cannot occur. In this view, reality exists because reality must exist. There is no alternative. The very concept of total nothingness may be logically unstable or incoherent. Some thinkers compare this to mathematics. Certain mathematical truths do not need causes. They simply follow from logical necessity. Likewise, existence itself may be a necessary feature of reality rather than a contingent one. The universe, or some deeper foundation beneath it, exists because non-existence is not a meaningful possibility. Others approach the problem differently. They suggest that the laws of quantum mechanics may make the emergence of universes inevitable. In quantum theory, events can occur probabilistically without classical causes. Tiny fluctuations constantly arise within quantum systems. If reality possesses a quantum foundation, perhaps universes naturally emerge from it. The appearance of existence would not require an external creator or prior cause. It would be a consequence of the underlying rules governing possibility itself. Yet critics quickly point out that this explanation does not eliminate the mystery. It merely shifts it. Why do quantum laws exist? Why is there a framework capable of generating universes? The deeper question remains. The search for answers often leads beyond science into philosophy. Throughout history, thinkers have proposed many solutions. Some argued that an eternal reality exists necessarily and serves as the foundation of all existence. Others claimed that existence requires a first cause existing outside ordinary space and time. Still others suggested that the question itself may be flawed because it assumes reality needs an explanation beyond its own existence. Modern cosmology has not resolved these debates. Instead, it has given them new forms. Scientific discoveries provide extraordinary insights into how the universe evolved, yet they have not eliminated the ultimate mystery of why anything exists at all. One reason this question remains so powerful is that it sits at the boundary of human understanding. Most scientific questions concern relationships between existing things. We ask how stars form, how galaxies evolve, or how particles interact. These questions can be investigated through observation and experiment. The question of why there is something rather than nothing is different. It concerns the existence of reality itself. There is no external vantage point from which to observe alternative possibilities. We cannot compare existence with non-existence because if non-existence truly occurred, there would be no observer to make the comparison. The mystery remains unique among all questions because it challenges the very foundations upon which questioning depends. Yet despite its difficulty, the question continues inspiring inquiry. Every generation of scientists pushes closer to the earliest moments of cosmic history. Telescopes peer deeper into space. Particle accelerators recreate conditions resembling the young universe. Mathematical theories explore realms beyond ordinary observation. Each discovery reveals new layers of complexity and beauty. At the same time, each answer often uncovers deeper questions. The closer we approach the beginning, the more mysterious the concept of a beginning becomes. There is something strangely comforting about this. Human beings often imagine knowledge as a journey toward complete understanding. Yet the history of science suggests a different picture. Every major breakthrough expands the horizon of mystery. The universe grows larger, older, and more complex. Rather than eliminating wonder, knowledge deepens it. The question of existence itself may be the ultimate example. No matter how far cosmology progresses, there may always remain a deeper layer beneath our explanations. The search becomes less about reaching a final answer and more about exploring reality with increasing clarity. If we return to the original question, what came before the Big Bang, we now see why it is so difficult to answer definitively. Even if we discover a previous universe, a multiverse, a quantum vacuum, or a higher dimensional realm, the mystery does not end. We must still ask why that deeper reality exists. The chain of explanation continues. Perhaps one day physics will uncover principles capable of addressing this question. Perhaps it will reveal that existence emerges naturally from deeper laws. Or perhaps the mystery will remain forever beyond complete understanding. For now, the possibility remains that before the Big Bang there was not another universe, another dimension, or another cycle. Perhaps there was something even more fundamental, the simple fact that existence itself is possible. Every galaxy, every star, every planet, every living creature, and every conscious thought traces its history back to that astonishing fact. The universe exists. And despite centuries of investigation, that simple statement remains one of the greatest mysteries humanity has ever encountered. The search for what came before the Big Bang continues. Some physicists have begun exploring a possibility so strange that it challenges our ordinary understanding of reality itself. What if the universe did not emerge from the past at all? What if the future played a role in shaping the beginning? In everyday life, cause always comes before effect. A stone falls because it is dropped. A tree grows because a seed was planted. Time appears to move in one direction, carrying causes forward into consequences. Yet the laws of physics are often far less rigid than our intuition suggests. At the deepest levels of reality, many equations work equally well whether time moves forward or backward. The mathematics describing fundamental particles frequently shows no preferred direction of time. This surprising symmetry has inspired some researchers to wonder whether the distinction between past and future is not as absolute as it appears. To understand why this matters, consider one of the great puzzles in cosmology, the arrow of time. The universe clearly evolves in a particular direction. Eggs break but do not spontaneously reassemble. Stars exhaust their fuel rather than becoming younger. Human beings remember the past but not the future. Physicists usually explain this asymmetry through entropy, the tendency of disorder to increase over time. Yet this explanation raises another question. Why did the universe begin in such an extraordinarily ordered state? The early cosmos possessed remarkably low entropy compared to what is possible. This initial condition appears highly unusual. Some scientists have argued that understanding the origin of this order may require rethinking our assumptions about time itself. One remarkable proposal suggests that the Big Bang was not merely a beginning but a kind of boundary separating two different temporal directions. According to this idea, time may flow away from the Big Bang in both directions. From our perspective, we inhabit one side of this boundary. We experience time moving forward as the universe expands and evolves. Yet on the opposite side, another universe could exist where observers also perceive time moving forward from their own perspective. To us, their universe would appear to move backward in time. To them, our universe would seem to do the same. Both civilizations would experience ordinary causality, memory, and history, yet each would occupy opposite temporal directions relative to the Big Bang. This concept is difficult to visualize because human intuition is deeply tied to a single direction of time. Imagine standing at the peak of a mountain. Two valleys extend away from the summit in opposite directions. From the summit itself, movement can proceed down either slope. Some physicists envision the Big Bang as a similar point. Instead of being the beginning of time, it becomes a central boundary from which two universes emerge. Time flows outward on both sides, carrying each cosmos away from the shared origin. The Big Bang no longer marks the start of everything. It becomes a symmetrical transition connecting two cosmic histories. If such a mirror universe exists, it might help explain several puzzling features of reality. Certain properties of fundamental particles display subtle asymmetries that remain difficult to understand. Some researchers speculate that opposite versions of these asymmetries could exist in the mirror universe, restoring a deeper symmetry across the larger structure. Likewise, the extraordinarily low entropy of the early universe might arise naturally if the Big Bang serves as a central point from which entropy increases in both directions. What appears highly special from our perspective could become more understandable within a broader temporal framework. Another fascinating consequence concerns causality. In ordinary experience, causes always precede effects. Yet some interpretations of quantum mechanics already hint at relationships that seem difficult to fit into conventional temporal order. Experiments involving entangled particles reveal correlations that transcend classical intuitions about space and time. While these phenomena do not permit communication backward through time, they demonstrate that reality possesses connections more subtle than everyday causality suggests. Certain theoretical models explore whether future boundary conditions could influence present events in ways that remain consistent with physical laws. Although highly speculative, such ideas encourage scientists to reconsider assumptions that once seemed unquestionable. The possibility of a time-symmetric cosmos also changes how we think about origins. Traditional questions assume that the universe emerged from a prior state existing in the past. But if time itself extends in opposite directions from the Big Bang, then asking what happened before may be misleading. There may be no earlier moment in the conventional sense. Instead, there are two futures unfolding away from a shared boundary. The Big Bang becomes less like the first page of a book and more like the spine connecting two sets of pages extending in opposite directions. Of course, these ideas remain speculative. Detecting evidence for a mirror universe beyond the Big Bang would be extraordinarily difficult. Researchers search for subtle clues in the cosmic microwave background, particle physics, and the large-scale structure of the cosmos. So far, no definitive confirmation has emerged. Yet the possibility remains scientifically intriguing because it arises from attempts to address genuine puzzles involving entropy, symmetry, and the nature of time. Unlike purely philosophical speculation, these models are grounded in mathematical frameworks that can, at least in principle, generate testable predictions. What makes this vision particularly captivating is the way it transforms the mystery of beginnings. Human beings naturally imagine time as a line stretching from the past into the future. The Big Bang appears as the first point on that line. But nature repeatedly teaches that intuitive pictures often fail at extreme scales. Earth is not the center of the cosmos. Space is not a rigid stage. Time is not an absolute universal clock. Perhaps the beginning of the universe is equally deceptive. The Big Bang may not be the first moment but a special boundary within a larger temporal structure that our minds struggle to comprehend. If this idea proves correct, then before the Big Bang there may not have been another universe in the traditional sense. Instead, there may be a mirror cosmos moving through time in the opposite direction. Its galaxies would evolve, its stars would shine, and its observers would ponder mysteries just as we do. From their perspective, they would inhabit the future. From ours, they would seem to belong to a realm beyond the beginning of time. Together, both universes would form parts of a larger reality whose symmetry extends across the very origin of existence itself. The Big Bang would no longer separate existence from non-existence. It would connect two vast cosmic histories unfolding forever away from a shared and mysterious source. If the previous ideas stretch the limits of imagination, the next possibility ventures into territory where the distinction between reality and information begins to dissolve. Over the last century, physicists have discovered something increasingly surprising. Information appears to be one of the most fundamental ingredients of the universe. At first glance, this sounds strange. Most people think of information as something stored in books, computers, or human memories. Yet modern physics suggests that information is woven into the structure of reality itself. Every particle carries information about its properties. Every physical process transforms information from one form into another. Even black holes, once thought to destroy information completely, are now believed to preserve it in ways that researchers are still struggling to understand. This realization has inspired a radical question. What if information is more fundamental than matter, energy, space, and time? What if the universe emerged not from physical substance but from information itself? The roots of this idea can be traced to discoveries involving quantum mechanics and black hole physics. During the 20th century, physicists came to understand that information obeys remarkably strict rules. In quantum theory, information about a system cannot simply vanish. This principle became especially important when researchers studied black holes. According to classical interpretations, anything falling into a black hole disappears forever, carrying its information with it. Yet quantum mechanics strongly suggests that information cannot be destroyed. This conflict became known as the black hole information paradox and led to decades of intense debate. Over time, many physicists concluded that information must somehow survive, even if the mechanism remains mysterious. The implication was profound. Information is not merely a useful description of reality. It appears to be a fundamental component of reality itself. As these ideas developed, some researchers proposed that the universe may be understood as a vast informational structure. Matter and energy become secondary phenomena emerging from deeper patterns of information. Just as images on a computer screen emerge from underlying code, physical reality may emerge from informational relationships operating beneath the observable world. In this framework, particles, forces, and space-time are not the ultimate building blocks of existence. They are manifestations of something more abstract. The universe resembles an immense informational network processing relationships according to fundamental rules. This perspective gained additional support from studies of quantum entanglement. Entangled particles display correlations that seem almost magical. Measuring one particle instantly reveals information about the other, regardless of the distance separating them. Although no usable signal travels faster than light, these correlations challenge ordinary intuitions about space and locality. Some physicists have suggested that space-time itself may emerge from patterns of quantum information. Instead of information existing within space, space could emerge from information. Distances, dimensions, and geometric relationships would then be consequences of deeper informational connections. If this is true, the entire universe may arise from structures far more fundamental than physical objects. When applied to the mystery of cosmic origins, the implications are extraordinary. The Big Bang would no longer represent the creation of matter from nothing. Instead, it would mark the emergence of a new informational structure. Before the Big Bang, there may have existed a deeper informational realm beyond ordinary space and time. Reality as we know it would emerge when certain informational patterns reached a critical state, generating the space-time framework within which galaxies, stars, and planets eventually formed. The beginning of the universe becomes less like an explosion and more like the activation of an immense informational process. Some researchers compare this idea to a hologram. A holographic image appears three-dimensional even though it is encoded on a two-dimensional surface. Surprisingly, theoretical studies of black holes have suggested that the universe itself may operate according to similar principles. Information describing a volume of space can sometimes be represented on a lower dimensional boundary. This concept became known as the holographic principle. If correct, the three-dimensional world we experience may emerge from information encoded on a more fundamental surface. Space itself becomes a kind of projection arising from deeper informational structures. The universe may be far less material than it appears. The philosophical consequences are profound. Human beings naturally think of reality as consisting of objects. We see mountains, oceans, stars, and planets. We imagine these things as fundamentally real. Yet the informational perspective suggests that objects may be secondary. What truly exists are relationships, patterns, and structures of information. Matter becomes a manifestation of information rather than its source. The distinction resembles the relationship between a book and the story it contains. The physical pages matter, but the deeper essence lies in the information encoded within them. This shift in perspective also changes how we think about existence itself. Traditional questions about origins often focus on physical substances. What material existed before the universe? What energy gave rise to the Big Bang? But if information is fundamental, these questions may need to be reformulated. Before the Big Bang, there may not have been matter or energy in any familiar sense. There may have been informational structures capable of generating physical reality. The universe would emerge when those structures produced the space-time framework we inhabit today. Of course, many aspects of this idea remain speculative. Scientists are still working to understand the precise relationship between information, quantum mechanics, gravity, and space-time. No complete theory currently explains how information could generate an entire universe. Yet the concept continues attracting attention because it offers new ways of approaching problems that have resisted traditional explanations. The connection between information and black holes, the holographic principle, and the strange behavior of quantum systems all hint that information may occupy a far more central role in reality than previously imagined. Perhaps the most fascinating aspect of this possibility is how it transforms our understanding of the cosmos. For centuries, humanity viewed the universe as a collection of physical objects moving through space and time. Modern physics increasingly suggests a different picture. Reality may be built from relationships rather than things, patterns rather than substances, information rather than matter. If this vision proves correct, then before the Big Bang there may have existed a vast informational realm beyond space and time. From that realm emerged the structure we call the universe, carrying within it every galaxy, every star, every planet, and every conscious mind that would eventually arise to wonder about its origins. In that sense, the story of cosmic beginnings may not be the story of matter appearing from nothing, but the story of information becoming reality. The 20th century gave way to the 21st. Cosmologists began confronting a realization that was both exciting and unsettling. The universe was not merely expanding, it was accelerating. Distant galaxies were moving away from one another faster than expected. Instead of slowing down under the influence of gravity, the expansion of space appeared to be speeding up. This discovery shocked the scientific community because it suggested the existence of an unknown component of reality. Whatever was driving this acceleration became known as dark energy. Today, dark energy is estimated to make up nearly 70% of the total energy content of the universe, yet its true nature remains one of the greatest mysteries in physics. Surprisingly, some researchers have wondered whether understanding dark energy may also provide clues about what existed before the Big Bang. To appreciate why dark energy is so mysterious, imagine throwing a ball into the air. Gravity slows the ball until it eventually stops and falls back toward the ground. For much of modern history, scientists assumed the universe would behave similarly. The expansion that began with the Big Bang would gradually slow as gravity pulled matter together. Depending on the amount of matter present, the cosmos might eventually stop expanding altogether. Some models even predicted a future collapse known as the Big Crunch. Yet observations revealed something entirely different. The universe was not slowing down. It was speeding up. Some invisible influence appeared to be overcoming gravity on the largest scales. The simplest explanation involves a property of space itself. According to quantum physics, even empty space contains energy. If space possesses a tiny intrinsic energy density, then as the universe expands and creates more space, the total amount of this energy increases. Unlike ordinary matter and radiation, which become diluted as the universe grows, this vacuum energy remains constant per unit volume. Over billions of years, its influence becomes increasingly dominant. Expansion accelerates. Galaxies drift farther apart. The cosmos enters a phase unlike anything experienced during most of its history. This discovery has profound implications for cosmic origins. If empty space contains energy capable of driving expansion today, perhaps a similar phenomenon operated in the earliest moments of the universe. In fact, many theories of cosmic inflation rely on exactly this idea. Inflation proposes that a special form of vacuum energy triggered an extraordinarily rapid expansion shortly after the Big Bang. Space grew exponentially, smoothing out irregularities and producing the large-scale structure observed today. But if vacuum energy can drive expansion, where does that energy come from? And could it have existed before the Big Bang itself? Some cosmologists have suggested that the universe may have emerged from a vacuum state far different from the one we observe today. According to certain models, reality can occupy multiple vacuum states, each with different energy levels and physical properties. Our universe may exist within one such state, but other vacuum configurations could have preceded it. A transition from one vacuum state to another might trigger the birth of a new universe. The Big Bang would then represent a phase transition, similar in some ways to water freezing into ice or steam condensing into liquid. Before the Big Bang, there may have existed a different vacuum environment with entirely different characteristics. This possibility becomes even more intriguing when combined with ideas from quantum cosmology. In some scenarios, vacuum states can spontaneously produce new regions of spacetime through a process known as quantum tunneling. Quantum particles occasionally cross barriers that appear impossible according to classical physics. Similarly, entire universes might emerge from one vacuum state into another. Our cosmos would be born as a bubble within a larger vacuum landscape. Outside our universe, other vacuum regions could continue existing, generating additional universes over vast stretches of time. Reality becomes a dynamic environment where cosmic creation is not a unique event but an ongoing process. The concept of a vacuum landscape gained particular attention within certain versions of string theory. These models suggest that an enormous number of possible vacuum states may exist, each corresponding to different physical laws and constants. Some estimates predict numbers so large that they defy ordinary comprehension. Within this vast landscape, universes continually emerge, evolve, and disappear. The Big Bang marks the beginning of our local cosmic region but not the beginning of the larger landscape itself. Before our universe formed, countless other regions may already have existed, each governed by different physical properties. Dark energy also influences our understanding of the universe's ultimate future. If acceleration continues indefinitely, distant galaxies will gradually disappear beyond our observable horizon. Trillions of years from now, observers may see only their local galaxy cluster surrounded by darkness. Eventually even stars will burn out, leaving a cold and increasingly empty cosmos. Some physicists call this scenario the heat death of the universe. Yet others wonder whether such an ending might somehow give rise to new beginnings. Could vacuum energy eventually trigger the birth of another universe? Might the future of one cosmos become the origin of another? These questions remain speculative, but they illustrate how closely cosmic endings and beginnings may be connected. There is a certain irony in this line of thought. For centuries, empty space was regarded as the absence of anything interesting. It was considered the background against which cosmic events occurred. Modern physics has transformed that picture completely. Empty space now appears active, energetic, and potentially creative. The vacuum is no longer nothingness. It is a dynamic component of reality capable of influencing the evolution of the entire universe. Understanding its nature may prove essential not only for explaining the future of the cosmos but also for uncovering its deepest origins. If these ideas are correct, then before the Big Bang there may not have been stars, galaxies, or even space-time in the form we recognize. Instead, there may have existed a vast vacuum landscape filled with hidden energy and countless possibilities. Our universe emerged as one transition within that landscape, expanding into the cosmos we observe today. The Big Bang would become not the absolute beginning of existence but one event in a larger process unfolding beyond the limits of our observable horizon. In that case, the ultimate answer to what came before the Big Bang may lie not in matter or time, but in the mysterious energy woven into the fabric of empty space itself. Cosmologists pushed their theories further into the unknown. Some arrived at a startling conclusion: perhaps the universe did not begin in a dramatic event at all. Perhaps the Big Bang only appears to be a beginning because of the limits of human observation. This possibility challenges one of the most deeply rooted assumptions in modern cosmology. We often imagine the Big Bang as a singular moment when everything suddenly came into existence. Yet there are theoretical models suggesting that reality may have no ultimate starting point. Instead of a universe with a beginning, there may be an eternal cosmos extending infinitely into the past, with the Big Bang representing only a local transition within a much larger history. The appeal of an eternal universe is easy to understand. One of the most difficult questions in cosmology concerns the problem of origins. Every explanation seems to require something preceding it. If the Big Bang created the universe, what caused the Big Bang? If another universe existed before ours, where did that universe come from? If a multiverse exists, how did the multiverse begin? The chain of questions appears endless. An eternal cosmos offers a way to escape this dilemma. If reality has always existed in some form, then there is no first moment requiring explanation. Existence simply is. There was never a time when reality did not exist. This idea is far older than modern science. Ancient philosophers debated whether the universe had a beginning or existed eternally. Some argued that creation from nothing seemed impossible. Others believed that an infinite past created logical difficulties of its own. These debates continued for centuries and eventually became intertwined with religious, philosophical, and scientific traditions. Even after the discovery of cosmic expansion, the question remained unresolved. Although the Big Bang theory successfully describes the evolution of the observable universe, it does not necessarily prove that reality itself had an absolute beginning. Several modern theories explore ways in which the universe could be eternal. Some involve endless cycles of expansion and contraction. Others describe a multiverse where new universes continuously form while the larger structure persists forever. Still others suggest that time itself behaves differently at the deepest levels of reality, making the distinction between beginning and eternity less meaningful than it appears. In certain quantum cosmological models, the universe may exist in a timeless state from which ordinary time emerges. From the perspective of observers living within the universe, history appears to have a starting point. Yet from a deeper perspective, reality may have no beginning at all. One fascinating approach comes from the concept of emergent time. In everyday life, time feels fundamental. Clocks measure it, memories depend on it, and physical processes unfold within it. However, some physicists suspect that time may not be a basic ingredient of reality. Instead, it could emerge from deeper relationships among more fundamental entities. This idea resembles how temperature emerges from the collective behavior of countless molecules. Temperature feels real, yet it is not a fundamental particle or force. Likewise, time may arise from underlying structures that themselves exist outside ordinary temporal order. If this is true, asking what happened before the Big Bang could be like asking what happened north of the North Pole. The question assumes a framework that does not apply at the deepest level. Another possibility involves infinite inflation. In certain versions of eternal inflation, new universes continuously emerge within a larger inflating background. Some cosmologists have explored whether this process could extend infinitely into the past as well as the future. If so, there would never have been a first universe. Every cosmic region would emerge from earlier processes stretching back without limit. Reality would resemble an endless tree with no root, only an infinite network of branching histories. Although mathematical challenges remain, the idea demonstrates how modern physics continues exploring alternatives to absolute beginnings. The notion of an eternal cosmos also raises profound philosophical questions. Human intuition often struggles with infinity. We are accustomed to beginnings and endings. Every life has a birth and a death. Every story has a first chapter and a last page. Applying these experiences to the universe feels natural. Yet the cosmos may not conform to human expectations. Infinity appears repeatedly throughout mathematics and physics. Space may be infinite. Time may be infinite. The number of possible universes may be infinite. Reality often proves stranger than common sense suggests. Critics of eternal models point out that infinity introduces its own difficulties. If the past is truly infinite, how did we ever arrive at the present moment? Can an infinite sequence of events actually exist in reality? Philosophers have debated such questions for centuries without reaching universal agreement. Some argue that an eternal past is impossible because it creates logical paradoxes. Others contend that these paradoxes arise only because human intuition is poorly equipped to handle infinity. The debate remains unresolved. What makes the idea of an eternal universe so compelling is that it transforms the mystery of origins. Instead of searching for a first cause, we begin asking different questions. Why does reality possess its particular structure? Why do physical laws exist in their current form? How do local beginnings emerge within a larger eternal framework? The focus shifts from creation to organization. Existence itself becomes the starting point rather than the problem to be solved. There is also a certain elegance in this vision. Throughout history, scientific discoveries have often replaced absolute boundaries with larger continuities. The horizon was not the edge of the world. The solar system was not the edge of the cosmos. The Milky Way was not the only galaxy. Perhaps the Big Bang is another example. What appears to be the beginning may actually be a horizon beyond which a deeper reality extends. The observable universe has a history stretching back nearly 13.8 billion years, but existence itself may reach far beyond that limit. If this perspective proves correct, then before the Big Bang there was not a void, a singularity, or a moment of creation. There was simply reality continuing in forms we do not yet fully understand. The Big Bang would represent a transition within an eternal cosmos rather than the birth of existence itself. Our universe would be one chapter in a story with no first page, part of a reality that has always existed and may continue forever. In that case, the greatest mystery may not be how the universe began, but why an eternal reality exists at all. After exploring quantum vacuums, cyclic universes, black holes, multiverse, higher dimensions, information theory, and eternal realities, we arrive at a remarkable realization. The deeper scientists investigate the question of what came before the Big Bang, the more they discover that the answer may depend on how we define reality itself. Every theory we have examined begins by challenging an assumption that once seemed obvious. Some question the nature of time. Others question the nature of space. Some challenge the idea of a unique universe, while others challenge the very concept of physical existence. Yet despite their differences, all these ideas share a common theme. They suggest that the universe visible through our telescopes may be only a small fragment of a much larger and more mysterious reality. This realization represents one of the greatest transformations in human thought. For most of history, the visible world appeared complete. The stars overhead seemed fixed and eternal. Earth felt central and stable. The cosmos appeared understandable through direct observation. Gradually, science revealed a different picture. The Earth became one planet among many. The Sun became one star among billions. The Milky Way became one galaxy among countless others scattered across unimaginable distances. With each discovery, humanity's place in the universe grew smaller while the scale of reality expanded dramatically. The search for what came before the Big Bang continues this tradition. It suggests that even the observable universe itself may not be the ultimate stage upon which existence unfolds. Consider how far our understanding has already progressed. Just a century ago, many scientists believed the universe was static and eternal. The discovery of cosmic expansion revolutionized cosmology. Observations of the cosmic microwave background confirmed that the universe evolved from a hot, dense state. Particle physics uncovered the building blocks of matter. Relativity transformed our understanding of space and time. Quantum mechanics revealed a microscopic world governed by probabilities rather than certainties. Each breakthrough opened new questions. The mystery of origin survived every advance, becoming more sophisticated rather than disappearing. One reason the problem remains so difficult is that human beings are attempting to investigate conditions far removed from everyday experience. We evolved on the surface of a small planet orbiting an ordinary star. Our senses developed to navigate forests, oceans, and landscapes, not to understand quantum gravity or the birth of space-time. Concepts such as infinity, higher dimensions, and timeless existence often seem strange because they lie far outside the environment that shaped human intuition. Yet history repeatedly demonstrates that reality does not conform to intuition. The universe behaves according to its own rules, regardless of whether those rules feel natural to us. This is especially true when discussing the earliest moments of cosmic history. The conditions near the Big Bang were unlike anything that exists today. Temperatures reached unimaginable extremes. Matter and energy merged into unfamiliar forms. Gravity interacted with quantum processes in ways that current theories struggle to describe. Under such circumstances, everyday concepts may cease to apply. Questions that appear straightforward from a human perspective may become meaningless at the deepest levels of reality. Asking what happened before the Big Bang may ultimately resemble asking what lies outside space or what occurred before time existed. The answer depends entirely on the underlying structure of existence. Yet uncertainty should not be mistaken for failure. In science, unanswered questions often mark the frontier of discovery. The fact that we do not yet know what came before the Big Bang does not indicate weakness. It reflects the extraordinary depth of the mystery. Humanity has already learned an astonishing amount about the cosmos. We can trace cosmic evolution across billions of years. We can detect light emitted shortly after the universe became transparent. We can study particles produced under conditions similar to those that existed in the early universe. Compared with previous generations, our understanding is remarkable. The remaining mysteries simply remind us that exploration is not finished. Future discoveries may dramatically reshape our picture of cosmic origins. A successful theory of quantum gravity could reveal what happens beyond the Planck epoch. New observations may uncover evidence supporting cyclic cosmology, eternal inflation, or higher dimensional models. Advances in particle physics could expose hidden structures underlying spacetime itself. Technologies not yet imagined may eventually provide access to information currently beyond reach. History suggests that many ideas once considered impossible later became accepted knowledge. The universe has surprised humanity before, and it may do so again. At the same time, there is value in recognizing that some mysteries may remain unresolved for a very long time. The question of what came before the Big Bang touches the deepest foundations of existence. It intersects with philosophy, mathematics, physics, and even questions about the limits of human knowledge. Different theories offer different answers, and each answer generates new questions. The search becomes not only an investigation of the universe but also an exploration of how understanding itself works. What kinds of questions can science answer? What assumptions shape our thinking? Are there aspects of reality that forever remain beyond observation? Perhaps the most important lesson is that the mystery of origins invites humility. Human civilization occupies a tiny corner of a vast cosmos. We have existed for only a brief moment compared with the age of the universe. Yet within that brief moment, we have learned enough to ask questions reaching beyond galaxies, beyond space, and perhaps beyond time itself. The ability to wonder about cosmic beginnings may be one of the most extraordinary achievements of conscious life. Whether the answer involves a multiverse, a quantum vacuum, an eternal cosmos, hidden dimensions, or something entirely unexpected, the search itself reflects humanity's deepest curiosity. As we conclude this stage of the journey, the question remains open. Before the Big Bang, there may have been another universe. There may have been countless universes. There may have been a timeless quantum realm, a multidimensional landscape, or an eternal reality stretching infinitely into the past. Or perhaps the concept of before simply does not apply. For now, no definitive answer exists. What remains is a mystery standing at the edge of knowledge, inviting future generations to continue the exploration. Somewhere beyond the horizon of current understanding lies the truth about what came before the Big Bang. Until that horizon is crossed, the mystery endures, vast and silent, waiting in the darkness beyond the beginning of time. Beyond the frontier of known cosmology, it becomes clear that one of the greatest obstacles in understanding what came before the Big Bang is not a lack of imagination, but a lack of a complete theory. Modern physics rests upon two extraordinary achievements: Einstein's general relativity and quantum mechanics. General relativity explains gravity, black holes, galaxies, and the large-scale structure of the universe. Quantum mechanics describes atoms, particles, radiation, and the microscopic world with astonishing precision. Both theories have been tested repeatedly and have survived every challenge. Yet there is one place where they refuse to cooperate, the very beginning of the universe. Near the Big Bang, matter becomes so dense and energies become so extreme that both theories must operate simultaneously. Unfortunately, when physicists attempt to combine them under these conditions, the mathematics breaks apart. Equations produce infinities. Predictions become meaningless. The universe vanishes behind a wall of uncertainty. This problem is not a minor technical inconvenience. It represents one of the deepest unsolved mysteries in science. Without a successful theory uniting gravity and quantum mechanics, our picture of cosmic origins remains incomplete. The search for such a theory has occupied generations of physicists. Some hope to achieve it through string theory, which replaces point-like particles with tiny vibrating strings. According to this framework, every particle in the universe arises from different patterns of vibration. Electrons, photons, quarks, and even hypothetical particles all emerge from the same fundamental entities. One of the most attractive features of string theory is that gravity appears naturally within its mathematics. Unlike many previous attempts, it offers a potential path toward quantum gravity. However, string theory introduces additional dimensions and mathematical complexities that make direct experimental confirmation difficult. Decades of research have produced remarkable insights but no definitive proof. The theory remains one of the leading candidates for describing conditions beyond the Big Bang, yet its ultimate status remains uncertain. Another approach, known as loop quantum gravity, takes a very different path. Instead of modifying the nature of particles, it focuses on space-time itself. In this framework, space is not infinitely smooth. It consists of tiny discrete units woven together into a quantum fabric. Distances and volumes come in fundamental increments, much like matter consists of atoms rather than continuous substance. Near the Big Bang, these quantum properties become extraordinarily important. The traditional singularity disappears because space-time cannot be compressed indefinitely. Instead of an infinitely dense point, the universe reaches a minimum size and then evolves according to quantum principles. Some versions of this theory predict a cosmic bounce, where a previous contracting universe gives rise to the expanding cosmos we observe today. If correct, the Big Bang would become a transition rather than a beginning. What makes the search for quantum gravity so important is that it may determine whether the question of before even makes sense. In everyday life, time appears continuous. One moment follows another in an endless sequence. Yet quantum gravity may reveal that time behaves very differently at the smallest scales. Some models suggest that time emerges from deeper processes and is not fundamental at all. Others imply that spacetime itself dissolves near the Planck scale, replaced by structures unlike anything familiar. Under such conditions, asking what happened before the Big Bang may resemble asking what color existed before colors were invented. The concepts required to frame the question may not apply. This realization has led some physicists to adopt a more cautious attitude toward cosmic origins. Rather than assuming the universe began in a singular event, they focus on understanding the conditions where current theories fail. History provides a useful lesson here. Whenever physics encountered infinities in the past, the problem usually indicated that an existing theory was incomplete rather than fundamentally correct. The ultraviolet catastrophe led to quantum mechanics. The orbit of Mercury helped confirm general relativity. Infinity surrounding the Big Bang may similarly point toward a deeper framework waiting to be discovered. The singularity could be less a physical object and more a signpost marking the boundary of present knowledge. Meanwhile, observational astronomy continues providing valuable clues. Telescopes capable of examining the earliest light in the universe allow researchers to study conditions remarkably close to the Big Bang. Experiments searching for primordial gravitational waves attempt to detect ripples in spacetime generated during the universe's infancy. Particle accelerators recreate tiny fractions of the energy present shortly after the beginning. Each new observation helps narrow the range of possible theories. Although we cannot directly observe what came before the Big Bang, we may infer aspects of that hidden realm through subtle signatures imprinted upon the cosmos we can see. The challenge resembles reconstructing an ancient civilization from scattered ruins. Imagine discovering fragments of walls, tools, and inscriptions buried beneath the earth. You may never witness the civilization directly, yet careful analysis allows you to infer its existence, culture, and history. Cosmologists face a similar task. The early universe left traces throughout the cosmos. By studying those traces, scientists hope to reconstruct events occurring at the dawn of time and perhaps beyond it. Every observation becomes a clue in an investigation spanning billions of years. There is also a deeper philosophical significance to this search. Human beings often seek final answers, definitive explanations bringing inquiry to an end. Yet science rarely works that way. Each breakthrough reveals new layers of complexity. Questions evolve rather than disappear. The search for quantum gravity illustrates this beautifully. It is not merely an effort to solve a technical problem. It represents an attempt to understand the foundations of reality itself. What is space? What is time? What is existence? These questions lie beneath every theory of cosmic origins. If a successful theory of quantum gravity is eventually discovered, it may revolutionize our understanding of what came before the Big Bang. Perhaps it will reveal a previous universe, an eternal multiverse, a timeless quantum state, or something entirely unexpected. The history of science suggests that reality often proves stranger than our most creative predictions. Whatever answer emerges, it is likely to challenge assumptions that currently seem obvious. For now, however, the boundary remains. Beyond the Planck epoch lies a region hidden behind the limitations of existing knowledge. It is a frontier where mathematics falters, intuition fails, and certainty disappears. Yet it is precisely this frontier that attracts some of the brightest minds in science. Somewhere within that hidden realm may lie the key to understanding not only what came before the Big Bang, but why the universe exists at all. Until that key is found, the mystery remains one of the greatest unsolved puzzles in human history. If there is one lesson repeated throughout the history of cosmology, it is that the universe is rarely what we first assume it to be. Every era believed it had reached the limits of understanding. Ancient civilizations thought the sky was a dome stretched above the earth. Later generations believed the stars were fixed lights attached to celestial spheres. Centuries afterward, many astronomers assumed the Milky Way contained all of existence. Again and again, reality turned out to be larger, stranger, and more complex than expected. This historical pattern raises an intriguing possibility regarding the Big Bang itself. What if future generations look back on our current understanding in the same way? What if the Big Bang, which now appears to be the ultimate beginning, eventually becomes just another chapter within a much grander cosmic framework? To appreciate this possibility, imagine living thousands of years ago and trying to understand the ocean while standing on a beach. The horizon would seem like a clear boundary. Beyond it, the world simply disappeared from view. Yet the horizon was never a true edge. It only marked the limit of observation. As ships traveled farther and navigation improved, entire continents emerged beyond what had once seemed like the end of the world. Cosmologists often wonder whether the Big Bang may represent a similar horizon. It appears to mark the beginning because it is the furthest point our current theories can reliably describe. But perhaps beyond that horizon lies an enormous realm of reality still hidden from view. This possibility gains strength from the remarkable success of scientific progress itself. Whenever humanity encountered an apparent boundary, deeper investigation often revealed a larger structure beyond it. The Earth was part of a solar system. The solar system belonged to a galaxy. The galaxy existed among billions of others. Space itself turned out to be expanding. The observable universe may even be only a small region within a far larger cosmos. Given this pattern, some scientists argue that it would be surprising if the Big Bang truly represented the final boundary of explanation. History suggests that boundaries often become gateways. One reason researchers remain cautious about declaring the Big Bang the absolute beginning is that many features of the early universe remain unexplained. Why did inflation occur? What determined the values of physical constants? Why does matter dominate over antimatter? What caused the remarkably smooth distribution of energy observed in the young cosmos? These questions hint that deeper processes may have been operating before the earliest moments we currently understand. The Big Bang Theory describes how the universe evolved, but it does not necessarily explain why those initial conditions existed. Some physicists compare the situation to reading a novel that begins in the middle of the story. Imagine opening a book and finding characters already engaged in complicated events. Relationships exist. Conflicts are underway. Important decisions have already been made. Although the story starts on the page before you, clues suggest that earlier chapters existed. The observable universe may be similar. Certain features of the cosmos appear so specific that they invite speculation about preceding events. The Big Bang could be the beginning of our observable chapter while deeper chapters remain hidden. The challenge is that any reality preceding the Big Bang may be extraordinarily difficult to investigate. Light cannot carry information from before the moment when space-time became transparent. Conventional observations eventually reach a limit. To move beyond that limit, scientists must rely on indirect evidence. Tiny patterns in cosmic radiation, subtle properties of elementary particles, and faint gravitational signals become crucial clues. Future instruments may reveal details currently beyond our reach. Entire fields of research are devoted to searching for these hidden signatures. There is also the possibility that the answer may require concepts not yet invented. Scientific revolutions often occur when entirely new frameworks emerge. Before Einstein, space and time were considered separate entities. Before quantum mechanics, probability played little role in fundamental physics. Future discoveries may introduce ideas that are currently as unimaginable to us as relativity would have seemed to medieval scholars. If so, the true nature of what came before the Big Bang may depend upon principles that have not yet entered human thought. This realization highlights an important aspect of science. Knowledge is not a static collection of facts. It is an evolving process. Questions that seem impossible in one century become routine in the next. The age of stars, the existence of galaxies, and the expansion of the universe were once unknown. Today they are foundational components of cosmology. Likewise, mysteries surrounding the Big Bang may eventually become understood within a broader theoretical framework. Future textbooks could describe pre-Big Bang physics as confidently as current textbooks describe planetary motion. Yet there is also beauty in uncertainty. The mystery of cosmic origins inspires exploration precisely because it remains unresolved. It invites creativity, debate, and discovery. Different theories compete, evolve, and occasionally merge. New observations challenge old assumptions. The search itself becomes a driving force behind scientific progress. Humanity learns not only about the universe but also about the methods used to understand it. Perhaps the most remarkable aspect of this journey is that conscious beings have emerged capable of asking such questions. Tiny creatures living on a small planet orbiting an ordinary star have developed the ability to investigate events occurring billions of years ago and billions of light-years away. We can reconstruct cosmic history, study the birth of galaxies, and contemplate the possibility of realities beyond space and time. This capacity for curiosity may be one of the universe's most extraordinary features. If future generations eventually solve the mystery, the answer may transform our understanding of existence as dramatically as any discovery in history. They may learn that the Big Bang emerged from a previous universe, a multidimensional landscape, a timeless quantum state, or something entirely unexpected. Or they may discover that the concept of a beginning is itself an illusion created by limited perspective. Whatever the truth turns out to be, it will almost certainly expand the boundaries of reality once again. For now, the Big Bang remains both a beginning and a horizon. It marks the start of the observable universe while concealing whatever lies beyond. Whether that hidden realm contains earlier universes, deeper laws, or entirely new forms of existence remains unknown. Yet the pattern of history encourages a certain optimism. Every time humanity reached what seemed like the edge of knowledge, a larger reality awaited beyond it. Perhaps the same will one day prove true for the greatest horizon of all, the mystery of what came before the Big Bang. By the time we reach this stage of our journey, the mystery of what came before the Big Bang has transformed into something much larger than a question about cosmology. It has become a question about the limits of knowledge itself. Throughout history, human beings have repeatedly encountered boundaries that seemed impossible to cross. There was a time when people could not imagine traveling beyond the horizon. There was a time when the stars appeared forever unreachable. There was a time when the existence of atoms, galaxies, black holes, and other worlds remained hidden from view. Yet each of those boundaries eventually yielded to curiosity, observation, and reason. The question before us now is whether the Big Bang represents another such boundary or whether it marks a limit beyond which understanding can never fully extend. The answer remains unknown, but the search itself reveals something profound about the nature of science and the nature of humanity. One of the most remarkable aspects of modern cosmology is how often it has forced us to abandon certainty. Every major breakthrough has challenged assumptions that once seemed self-evident. Space was not fixed. Time was not absolute. Matter was not solid. The universe was not eternal in the way many had imagined. Even reality itself became stranger as quantum mechanics revealed a world governed by probabilities rather than simple determinism. These lessons encourage caution whenever we feel tempted to declare a mystery permanently unsolvable. The history of science is filled with questions that appeared impossible until new ideas emerged. The Big Bang may eventually prove to be another example. Yet there is a crucial difference between ordinary scientific mysteries and the question of what came before the Big Bang. Most scientific investigations examine events occurring within the universe. Researchers study stars, planets, particles, and physical processes that exist inside space-time. The mystery of cosmic origins is different because it concerns space-time itself. We are attempting to understand the framework within which all observations occur. This creates a unique challenge. Every experiment, every telescope, every measurement depends upon the existence of the universe. There is no external laboratory from which we can observe reality being created. We are inhabitants of the system we are trying to explain. This limitation has inspired some philosophers and physicists to wonder whether certain aspects of cosmic origins may remain permanently inaccessible. Perhaps there are truths about the beginning that no observer within the universe can ever fully discover. Imagine a character living inside a novel attempting to understand the process by which the book was written. No matter how intelligent the character becomes, certain aspects of authorship may remain beyond reach because they exist outside the framework of the story itself. Some researchers speculate that humanity may face a similar situation. If the origin of the universe involves structures beyond space and time, then complete understanding may require perspectives unavailable to beings embedded within space-time. However, history offers reasons for optimism. Again and again, reality has revealed hidden pathways into seemingly inaccessible domains. Black holes were once considered completely unknowable, yet modern physics has uncovered remarkable details about their properties. The interior of atoms appeared forever beyond observation, yet quantum mechanics revealed their structure. Even the early universe, once thought inaccessible, now leaves observable traces in the cosmic microwave background and the large-scale distribution of galaxies. The lesson is clear. Apparent impossibility does not always indicate a true limit. Sometimes it reflects only the current state of knowledge. Future generations may possess tools beyond anything we can presently imagine. New forms of observation could reveal signatures from epochs currently hidden behind the Big Bang. Advances in quantum gravity may provide mathematical frameworks capable of describing conditions where existing theories fail. Artificial intelligence, quantum computing, and technologies not yet conceived may allow scientists to explore realms that remain inaccessible today. The history of science suggests that the future often arrives with surprises no one anticipated. There is also a deeper reason why the mystery of origins continues to matter. Understanding what came before the Big Bang is not merely about satisfying curiosity. The answer could fundamentally reshape our understanding of existence. If the universe emerged from a quantum vacuum, then reality may be rooted in probabilistic processes. If a multiverse exists, our cosmos may be one among countless others. If space-time emerged from information, then information may be more fundamental than matter. If time itself began with the Big Bang, then causality may have limits. Every possible answer transforms our view of reality and our place within it. The search also reveals something important about human nature. Unlike other known forms of life, humans do not simply inhabit the universe. We attempt to understand it. We ask questions that extend far beyond immediate survival. We investigate events occurring billions of years before our species existed. We construct theories about dimensions we cannot see and realities we cannot directly observe. This drive to understand may be one of the most extraordinary products of cosmic evolution. The universe has produced beings capable of reflecting upon the universe itself. Perhaps that is why the mystery of what came before the Big Bang feels so compelling. It sits at the intersection of science, philosophy, and imagination. It forces us to confront questions that have fascinated thinkers for thousands of years. Why does reality exist? Is there a beginning? Are there limits to knowledge? What is the true nature of time, space, and existence? These questions remain open, inviting every generation to contribute new ideas and perspectives. As we stand today, the answer remains hidden beyond the horizon of current understanding. The Big Bang marks the earliest chapter we can confidently reconstruct, but whether it represents the first chapter of all existence remains uncertain. Beyond that boundary may lie another universe, a quantum realm, a multidimensional landscape, an eternal reality, or something entirely beyond present imagination. The possibilities remain vast. And perhaps that is fitting. The greatest mysteries are not valuable because they provide immediate answers. They are valuable because they inspire exploration. They encourage humanity to continue questioning, observing, and discovering. The mystery of what came before the Big Bang has already transformed cosmology, driven new theories, and expanded the limits of thought. Whatever the final answer turns out to be, the search for it may prove just as important as the answer itself. For in seeking the beginning of everything, humanity learns not only about the universe, but about its own endless desire to understand the unknown. After exploring every major theory, every possibility, and every mystery surrounding what may have existed before the Big Bang, we arrive at the edge of a profound realization. The ultimate answer remains unknown. Yet perhaps that uncertainty is not a flaw in our understanding but a reflection of the extraordinary depth of the question itself. Throughout this journey, we have traveled through quantum realms, eternal universes, higher dimensions, cosmic cycles, black holes, multiverse, informational realities, and timeless mathematical landscapes. Each theory offered a different window into the unknown. Some suggested that another universe existed before our own. Others proposed that time itself began with the Big Bang, making the idea of a before meaningless. Some imagined reality as an endless ocean generating universes without end. Others pointed toward structures so abstract that they seemed to exist beyond space, time, and matter altogether. Yet despite their differences, all these ideas share a common truth: the universe is far stranger than human beings once believed. For most of human history, the night sky inspired myths and stories. Ancient civilizations gazed upward and saw gods, spirits, and celestial kingdoms. Later generations replaced myths with astronomy, discovering planets, stars, and galaxies governed by natural laws. Then came relativity and quantum mechanics, revealing a universe where space bends, time slows, particles behave like waves, and empty space is never truly empty. Each scientific revolution expanded reality beyond previous imagination. What once seemed impossible became accepted knowledge. The lesson is clear. The universe repeatedly exceeds the limits of human intuition. The mystery of the Big Bang may represent the next great frontier in that long tradition of discovery. Today, the earliest moments of cosmic history remain hidden behind a veil that current theories cannot fully penetrate. We can reconstruct events that occurred fractions of a second after the beginning. We can observe ancient radiation that has traveled across billions of years. We can calculate the evolution of galaxies, stars, and planets with remarkable precision. Yet beyond a certain point, our equations fail. The trail disappears into darkness. Somewhere beyond that boundary lies the answer to what came before the Big Bang, if such an answer exists at all. Perhaps future generations will solve this mystery. They may develop a successful theory of quantum gravity capable of describing the birth of spacetime itself. They may discover evidence for a previous universe, a multiverse, or hidden dimensions. They may uncover entirely new principles that transform our understanding of existence. History suggests that the future often contains ideas that are impossible to predict from the perspective of the present. The answer, when it finally arrives, may be something no one alive today has imagined. Yet there is another possibility. The question may lead us toward a deeper understanding of knowledge itself. We may discover that certain mysteries cannot be fully resolved from within the universe. Just as a character inside a story cannot completely step outside the book to observe its author, conscious beings living within space-time may encounter limits when attempting to understand the origin of space-time. If such limits exist, they would not diminish the value of inquiry. On the contrary, they would reveal something important about the relationship between observers and reality. What makes this mystery truly remarkable is not simply its scientific significance but its human significance. The atoms in our bodies were forged inside ancient stars. Those stars formed from material created in the early universe. Every living thing on Earth traces its history back through cosmic evolution to the conditions established near the beginning of time. When we ask what came before the Big Bang, we are ultimately asking where our own story begins. We are seeking the deepest roots of existence itself. There is a certain beauty in recognizing how far humanity has come. On a small planet orbiting an ordinary star in the outskirts of a galaxy among billions, intelligent beings emerged capable of asking questions about the origin of the cosmos. We have built instruments that can observe light emitted billions of years ago. We have developed mathematics capable of describing black holes, quantum fields, and cosmic expansion. We have learned enough about the universe to realize how much remains unknown. That awareness of mystery is itself a remarkable achievement. As we conclude this journey, the darkness beyond the Big Bang remains unexplored. Perhaps it contains another universe. Perhaps it contains an infinite multiverse stretching beyond imagination. Perhaps it contains a timeless quantum reality from which all universes emerge. Or perhaps the Big Bang truly marks the beginning of time itself, making the search for an earlier moment impossible. For now, we do not know. And yet, in a sense, that is what makes the mystery so powerful. The universe does not owe us simple answers. It reveals its secrets slowly, one generation at a time. Every discovery opens new questions. Every horizon conceals another beyond it. The search continues, carried forward by curiosity, imagination, and the desire to understand our place in existence. Somewhere beyond the first light of the cosmos, beyond the birth of stars and galaxies, beyond the limits of current knowledge, the truth waits. And until that truth is found, the mystery of what came before the Big Bang remains one of the greatest stories ever told, a story still unfinished, still unfolding, and still inviting humanity to look beyond the beginning of time itself.